Good morning, ladies and gentlemen, esteemed guests and workshop participants. Welcome to 4th day of GIAN workshop on advanced functional materials and green energy strategies. I once again welcome Professor P.V. Kamath, sir. We are delighted to have you back for another day of insightful lectures as we continue our GIAN workshop lecture series. As you may recall, we were fortunate to have the privilege of listening to a thought-provoking and inspiring presentation by Professor P.V. Kamath, sir.
This session will be chaired over by Professor S.S. Kodekar, sir, Department of Chemistry. He is Senior Professor at Department of Chemistry. More than 20 students awarded PhD under his guidance. Currently, 5 students are working in his research group. I may invite Professor S.S. Kodekar, sir, to take a charge and continue.
Let's start. Okay. This was yesterday because of a thing. I was supposed to give it yesterday morning, and I decided to give it now, and at the end of it, we'll talk about some research opportunities. That is the main title of this talk. Okay. This is on perovskite solar cell. It got clipped on the top. Let's go. Okay, I showed this slide and we discussed it. As you may recall, this area of nanomaterials for energy conversion has expanded in such a way it's very difficult to go in detail. So you may need a month long to go every part to do this one. And what I try to do my best is to give you an overview how the field started and how the status of current status, right? So if you are working in any one of this area, you need to explore. And as I also mentioned, things are getting harder now because anywhere you go, there are thousands of people working on a very similar materials, same trying to address the problem. So it puts an additional challenge how to make the work we do can stand out, right? So we first went with nanomaterials, both semiconductor and metal particles, their synthesis, their properties. Then we've studied liquid junction solar cells, thin film solar cells. Then also we did 2D materials yesterday, and also photocatalysis. The one thing I didn't touch is the batteries, right? So probably somebody else will talk tomorrow. They will tell you. So all these materials are being explored for addressing our energy challenge. So again, there are new materials are coming out showing new properties. And one such material came out about 10-15 years back, was called metal halide perovskites. So we are going to talk about it, these ones. And this is what you get from the what we call thin film solar cells. Professor Patil mentioned about thin film solar cells. There is an NREL chart. They puts out these numbers. Okay, so we analyze those numbers based on area, certified efficiencies, VOCs, fill factor, and which group did it. Okay, so the way we started in 90s was dye-sensitized solar cell. Until then, only PVs and maybe SIGs type materials were used. And from that, this was a liquid junction cell. Then we started solid-state dye-sensitized solar cell. Instead of redox couple, people use hole conductors. Then we went to this quantum dot solar cell or extremely thin absorber cell where like you can use Sylar method and make these thin film solar cells. As you can see here, over the period, the thickness started dropping and the perovskite solar cell are less than a micron thick. Okay. Again, Professor Patil mentioned the silicon wafers are typically like 10 microns. So again, it gives you less materials can used for the solar cell made it. And these are the certified efficiencies. That means in the lab you make a cell, you send it to an independent party, they measure it. So it's not what you measured in your lab, they measured it, they calculate the area of the cell, they get the power output, and you know how much photon you're putting one sun. One sun is typically, it's called 100 milliwatt per centimeter square. And you take your solar cell under the same condition. If you take a 1 centimeter square cell and you get 10 milliwatt out of it, right? That means your cell is 10%. So there is a Shockley quasar limit. It says the maximum you can get on a single junction solar cell is 33%. That is because your band gap and the light absorption properties. Everything is less. So it's very difficult to get 33. If you get silicon, it's about 28% maximum in the lab. So again, people have trying to do with perovskite. They have gotten up to single junction. This should be 26.1%, not 21.6. Okay, here it is, 26.1% for single junction. But you see the area of the cell, 0.05 centimeter. Think about 0.05, how much? What's the approximately? 0.2 millimeter by 2 millimeter will give you 0.04. It's slightly more than 2 millimeter. I don't know how accurately they can measure the area, but they certified it, they got this value. Same thing if you make it 1 centimeter square, that's what the efficiency is. So this is where the problem is. If you start making larger panels, this is going to drop down further. Silicon solar cell, I said 28%. That's about 1 centimeter square. But if you make it large panels, they go anywhere from 15 to 20%. So why the efficiency is important? Why it is important? Because for a given area, if you have a fixed rooftop, if the efficiency is higher, you can draw more power out of it. So if you are sending satellite, your area is limited, how much area you can get. And they want to generate, and they're the generate is, they want maximum. So they use the multiple junction, and they don't care about how much it costs. But they want like 45% efficiency, because then they can get more power out of it, okay? When the first rocket sent by Russia, it was a battery powered, Sputnik. And once the battery died, it died too, right? So same thing I say about the car. In the modern car, you see all these fine gadgets, right? But if your battery is dead, it doesn't matter. If your phone is just doesn't have power, it's as good as a stone sitting outside. It doesn't work. So that's why I always say electrochemistry rules the entire world. So when somebody says electrochemistry is a old field, that's not interesting, tell them that take out the battery from your phone and then see what happens, right? Okay, anyway, so that's about the efficiencies, how it is done. And again, these are the parameter. Another parameter people look for is the voltage, how much voltage you can get. So for example, your battery cells are like 1.5 volts, right? And everything is a multiple. Lead acid battery, each compartment is 2 volts. There are 6 compartments. So you have to get combination in parallel and series to match the whole thing. So that's why the voltage becomes very important. The fill factor is, again, how much efficiently you can do. It's a short circuit current times voltage is your maximum limit, right? And this measure the maximum output divided by the current and voltage will give you the fill factor. Anyway, so we published an article analyzing the efficiency called "Are Perovskite Solar Cell Reaching the Efficiency Voltage Limit?" I will come back to you that one. Okay, what is a metal halide perovskite, right? So it is started with the name guy called Perovsky. So they found a mineral like a strontium titanate, and I don't know exactly what he found, but it's like strontium titanate is a perovskite. They have a defined structure where any material with the same type of crystal structure as calcium titanium oxide, CaTiO3, known as the perovskite structure ABX3, right? And first discovered by this Rose in 1839 and named after Russian mineralogist Perovsky. And that's the crystal structure of it. This is A is one cation, B is another metal ion, and this one is O. And this is what it is known until about 1990s, and then they replaced this one with a halide ion. And that become metal halide perovskite. And why it drawn so much attention? Again, they were used for solar cell, low temperature processing, earth abundant materials. Their prototype is like, here the cation could be an organic cation. And there are only three cations that works. One is methyl ammonium, cesium, and formamidine. And essentially, it has to get inserted within these lattice, these cations. So they are not coordinated. And that is the weak point of it. If they really had a strong chemical bond, they would have been strong. So they can be exchanged. I will show you how these ions come out and go later on. They have this crystal structure, and that's what this methyl ammonium, and this can be replaced by cesium or formamidine. So this is the efficiency charts. It started growing up. There may be one more. And when you make solar cell, okay, here it is. Okay, this is cross section of the solar cell that we have, and remember, you make FTO electrode, conducting glass electrode, used all the time. If you take a cross sectional image, that's the big crystals you see here, they are your FTO, whatever that is, conducting tin oxide layer. Look at the thickness here, okay? And on that one, you are putting a colloidal TiO2 just to break the barrier of FTO. Then you are putting a mesoscopic TiO2, and on that one, you are putting methyl ammonium lead iodide. And that's what the thickness is. This is your whole conducting layer. In this case, it's spherometide, and on the top, there is a gold contact. So if you see it, your entire thickness of all these layers is almost same as your FTO layer, less than a micron thick. So that is the beauty of it, because you can do this thin film deposition and get it, and that this one. And we make the solar cells like this, test it, or at least we used to, and then you can analyze with the JV curves, we call it. It's basically how the voltage responds when you start making current, right? The largest current you can get, what we call short circuit current, is when there is no resistance between the two, right? Or the minimum resistance. So at that time, your voltage drops to zero. But what you do is you take it, and typically in olden days, what we used to do is we used to change the resistance between your two electrodes and measure your voltage. And if you know the resistance, you can calculate the current, right? So V equal to IR. So we used to write it down and do it. And that is the right way to do it in the steady state, because you are giving time to equilibrate, change the resistance, record it, and get these curves, and you will get the same points. What nowadays we do is we have potentiostats. They can be driven by computer programs. So we said, okay, scan between this potential to this potential. No one knows how it works, right? When they scan this potential. What it's actually doing is it is decreasing the resistance. It's changing the potential means it is decreasing the resistance between the two electrodes, and then it is scanning it. Sometimes people scan it beyond zero, right? It is an instrument. It will do whatever you want to do. But there is no meaning for this side or if you go down here, although you will get the values. And sometimes people still put it to, because instrument gave them the value. So again, that's the real way, because if you do manually, these are your limits. Okay, so again, from there, people have made now tandem solar cells and other things. Okay, how it all started, right? We all think it started yesterday. But in 90s, there is a David Mitzi. This is in early 2000, 1990s to 2000. He was in Bell Labs. Right now, he's in Duke. Their team published several papers. And these were, this one, they use tin metal halide. They use this one, another tin, gallium, germanium, tin, lead, different ones. So all these things they were doing it. But their interest was trying to applications in OLEDs and transistors. They never explored its solar cell or photovoltaic properties. Most of their focus was on trying to make transistors, because Bell Lab was exploring the transistors' properties, see whether they can work for a transistor. They also tried to use for LEDs, and it didn't work very well, right? But they still published very good journal papers, and it exists. And then in 2000 to 2009, converging fields, right? So this Tom Miyasaka, he made a liquid junction solar cell with methyl ammonium lead iodide and bromide solar cells. And he had published at conferences. Nobody paid attention because you got a couple of milliamps. That's his data here, you can see here. And it did not last. Within 5 minutes, it was dead, right? Because it corroded in the solvent when you shine the light. So the first solar cell, that's a Jack's paper he published. And at the same time, Namgyu Park also published, and he called it as a perovskite quantum dot sensitized solar cell. So it was just evolving. So again, both were liquid junction solar cells at the time. Then came in 2012 a major turning to solid state. Okay, so initial attempt with the polypyro, and so they published here this one, and you can see the efficiency was 0.21%, not 21%, 0.21%. See, when you are starting a field, how it gets. Then there were two papers came almost at the same time, one by Michael Gretzel and Namgyu Park, and they were in a hurry to publish. They published in scientific reports. And Henry Snaith and Miyasaka and others, they published with percentage with 10.9% in Science. And I think now you see the thing. This got published first, then this got published. Okay, this was published in, I think, around June of that year, and this was published in September of this year, August or September. But this is the publication day, submitted. This was submitted on May 31. My guess is somebody told them that, well, this group has been working and these guys are all working, let's get it quickly published. And they submitted in July 5, and they got published first. So again, one need to see when you receive it. So today, if you really want to get a date stamp on your work, submit to archives journals. There is a Chem archive, there is an archive, bioarchive. So these are called preprint servers. They are not reviewed. But you can show that, well, I submitted this paper. Even the journal rejects. See, once the journal rejects, you lose the date stamp, right? Suppose I submitted to Nature and it get rejected, and today's date. So it comes back after another 2 weeks. Then I submit to another journal. So I lose a month, right? But if I put in a preprint server, I already know that I prepared this work on this date. So for any patent rights or any other things, you can use it. And when you put it in a preprint server, you get a DOI number. So you can even cite it. So again, just I'm telling you, so if you want to see before publication, you can just send it and somebody looks at it and then they post it. It is not reviewed, there is no comments. Sometimes other people see that paper and they might send you the comments. So sometimes it helps if someone sees it and they can give you feedback. So there is lots of people putting it. Started first with archive, which was in Cornell University. Then they started Chem Archive, which is supported by several societies. So again, keep in mind, if you want to protect your date of submission, this is not a bad idea. And today, almost all journals, like about 10 years back, the journals didn't take it. If you already put it on the website, on an archive, they say, we don't want your paper because you already published it. But today, they all accept it, okay? Only thing is that you have to tell that, well, we have submitted into archive too. And when you do this cross-check for similarities, we get with 90%, 95% similarity. And right away we know it is one of the preprint server, it crawled in. Okay, one of the thing interesting was Snaith's alumina. He used, instead of TiO2 and alumina, he both, right? So just to show that it works both with these things, and although nobody is using alumina now, at that time it made a thing that all these electrons were traveling like this and the holes were traveling in the opposite direction, so it did not need TiO2. And they got very high voltage to begin with. A band gap was 1.55 and you can get up to 1. Today we can get up to 1.2 volts, okay? Why does this work at that time? And they came back, again, new era. This is published in 2013. The results took us by surprise. Not only was the charge transport faster and the photocurrent unaffected when the TiO2 is replaced by the alumina, but for a like-to-like comparison, the open circuit voltage increased by 200 millivolts. So again, that's the Henry Snaith, he put it. Again, these are the open circuit voltage for different semiconductors, and this is the optical band gap. And as you can see here, these are the different lines, and the perovskite is way up on the top. That means your voltage loss is much less in this material. And again, in the Nature's top 10, they made it methylammonium iodide, and already has an efficiency 15%, the iodide iodide. The performance has very quickly got to a high level, said Richard Friend. This was a breakthrough of the year, and these were all, this is Sangul Suk from Korea. So all these people sort of instrumental in the beginning. And then there was sort of a race to show I can make a higher efficiency cell. And this was paper by Yang, and it got a lot of criticism because they published in the Science, and they claimed an efficiency very high, 19.3%. However, that didn't last long. The stability was like maybe 20 seconds or something, right? When you make it first, they show it, then they do it, they got these curves and everything. They reported, again, that's their solar cell distribution efficiencies and this one. See, the time versus PCE, within how quickly they dropped efficiency. So they were not stable at all when they made it. Although they claimed high efficiency, it was not stable. It was just when you turn on the lamp, that's what they show. Okay, how to make them, right? Again, this is just very simple way. When we started, you just mix lead iodide and methylammonium iodide in fluorobenzene. This is one of the methods. Now people use DMF, other solvents too, and stir for 2 hours at 70 degrees. A yellow colored solution forms. that's an iodide complex. Okay, with excess iodide, it becomes yellow. Otherwise, PbI2 is not that colored. We have looked more into these complexes and other things. And then you put a drop on your spin coater and spin it. And you get a yellow film, and you can see the darkness is coming. And you put on a hot plate about 60 degrees to 80 degrees, it turns black. Okay, so your yellow film, and that is the conversion from lead iodide complex into this one. Actually, when we saw this color change, right away the question was, how does it change, right? We had 2 or 3 papers just studying various aspects, crystallography, and it was very early times. So this is how to pick a research problem. When you see something, and try to do it. Because if I do it today, nobody cares. Because when something is hot, you try to understand what it is, and we have done it. So the other method is 2-step. You can spin coat this one, you dry it. People have dipped it in this vapor, or you can also subject to the vapors of some these methyl ammonium salts away, and then anneal it. Over the years, there are several variations of these 2 approaches with claims of high quality films. This is one thing you see in the papers, right? I added ABC compound and my films are better. I got a better grain size, right? So how reproducible is it in other labs? So there is, the most common methods are fine, okay, in this one. And then planar cells without mesoscopic also perform quite efficiently. You don't need even that TiO2 layer, but it helps stability. Again, this one, even it continues and has been shown to be, they have got now triple cation. They add all 3, this one, and formamidine, right? That gives you stable structure, because when you add cesium, it little bit contracts the lattice, and your lattice is more rigid. Okay, design of perovskite solar cell, device components. You have optically transparent electrode, then you have electron transport layer, then you have perovskite absorber that you deposit on the top of it, then you have a whole transport material, HTM, and then you have got a gold counter electrode. That's it. So you put layer by layer each step and do it in this one. And then you shine the light, and what happens is you generate this charge carrier, charge separation, and electron goes to the one side, holes goes towards HT, whole transport layer, and that's it. This is one of our students, the CNE News magazine, when we were working. There were nobody working in the, maybe in NRail somebody, but we were one of the early ones got involved, and CNE News got in. You want to play the video? See whether it plays. He was a very talented student, Joe Mansell, and when we were working, we didn't know how to do it, and then look how bad these films were when we made. They were not that. This is Jeff Christians. This is the Mercury Canadian. These solar cells are photovoltaics, but typically made in a way by layer and especially for the transport. This particular lab shoots the coated glass with a dense layer obtained by us to prevent electrical charge being by sunlight from leaking out of the cell. This robotic by spraying contained dioxide solution of the glass. Next,
A less dense porous oxide covers the dense oxide. Usually it's contained by oxide, but other oxide can be used as well. A simple high-speed spin motor deposits the solar in solution and spreads it evenly across the device. Heating it up conditions for solar systems. Next up is the peroxide, which works especially long range in solar cycle. To compare the peroxide used in this research schematics for a person with surface, lead oxide, and methyl. They drip the liquid-based mixture with some oxide polyamines and give it a sieve to spread the film in the front. Now comes the color-coordinated fiber. It only takes an ordinary lamp popcorn. Gently heating the except applying the lights should spontaneously crystallize the persons with a freshly positive rainbow. This is the form of methyl lead iodide, which stops the aluminum peroxide crystals.
So you can see it is a real time changing the color.
It's easy to know that the persons undergo crystallization, color gains, realities. After completing a few more steps, the device is ready to test. Hook it up, turn on a solar simulator, such as fingerprints, and wow, this little device transforms light energy to electricity. We probably will find peroxide solar cells and rotor crystals in large crystals. But judging from the recent explosion in research popularity, these low-cost photovoltaic cells are likely to show us light. For chemical engineering news, I'm Shivaji.
Okay. So this was done, I think, around 2014, 15-ish, okay? It's an old one, so when you started new. But it also gives you an idea how to make these solar cells. Again, thin film solar cells, again, we learned from scratch. When we were coming from this liquid junction background and we were trying to make it, and reproducibility, one day we'll get 2%, another get 6%, whatever thing. We were going crazy. So Joe Manser, I met Namgyu Park, and he went to his lab in Korea, spent 2 weeks, learned all the tricks. That was nice of the Namgyu Park to teach us. And he came in, and voila, that's a day and night difference. We can make consistently about 15% cells at that time. And this is how we have to do it. If you don't know something, go to another lab, learn something, and bring back information. And then we volunteered, and then a lot of other people within the US and Canada, they wanted to come and do it. At least half a dozen groups. They came to our lab. They spent 2 or 3 days. They made same cells. And this is what the reproducibility should be and how science should be propagated. It's not that my own secret, I'm not going to let you. Because if you are coming, we should be able to give openly. So that has been my philosophy. We are in the early times when you make these nanoparticles, we put recipes, we call synthetic secrets, and put all the recipes, exactly how many milliliters. And what happened is that method becomes a standard method. Everybody uses the same method, so it propagates. So these are the advantage one has to do it. Again, you put these layers, I showed you this cross section earlier, and you make these cells and test it. And again, you develop EQE or IPCE, you get about 90% in this. We use a copper iodide. We wanted to do something different, right? So immediately what you do is you change a hole conductor. Instead of organic, we said we'll use inorganic hole conductor. That's our first attempt, copper iodide, and we showed how it compares. The voltage was much less, but it was more stable. And so again, we got it, and initially we submitted the paper to Nanoletters, and they rejected the paper, okay? Editorially rejected. And later on we submitted to JAX, we got good reviews and published. And for that year, it was a highly cited paper in JAX, this one. So don't get discouraged if your paper gets rejected. Your research is fine, someone didn't read it carefully, send it to another journal and get it published. Again, when we made this cell, it is, you may laugh at it today when you look at it, but at that time, for us, it was significant, right? We showed that an inorganic semiconductor can be used. doing it again in this early work. Again, there was optimizing cell performance, and we went up to 13% at that time. This is about 2014, 15-ish. Then we got 16%, and we make it between 18 to 20% now. But the other rest of the world was going much faster than we can catch up, right? So the thing is we don't want to be the followers. We want to do something else. So we basically sort of slow down our solar cell research and divert it into understanding more of the other phenomena that are contributing to these solar cells, okay? So another thing also we did was Jeff Christians, we did a lot of standardization. So in the sense that how to correctly identify the processes or measure things, what kind of scan rates, what kind of intensity, all these things, some of the things. And so today, and you can see here, what I told you was so far from here to about here, right? So we reached already, you can see here, in 2018, the efficiencies reached about 23-24%, certified efficiency. This is the era where efficiency was the major dominant factor in solar cell. You see it now after 2019, less than 1% increase. So if you are working on a solar cell efficiency, again, this is my take, don't waste time on claiming high efficiency, because looks like the efficiency is all saturated. Okay, it's plateaued. You can see here. Even the last one, they went from 26 to 26.1. All other characteristics are same except the efficiency, which is 26 and 26.1. How did they get it? They went from 0.1 centimeter square into 0.05 centimeter square. So that's not the thing. We have seen only small increases. The 0.1 centimeter area exhibits relatively greater efficiency, and this is now champion efficiency, right? Than the PSC with 1 centimeter square. If you go into the same table, we get about 21.6%. It is interesting to note that this record efficiency remains unchallenged since 2019 in this chart. A recent report claims 24.35. It is still less than 26.1. So if you are making 1 centimeter square and you are not getting high, that is one of the reasons. Okay. Again, tandem solar cell have reached up to 33.7% in this one. And this is where if you plot efficiency versus the area, there are two classes. One is about 1 centimeter square. This is what we started with earlier. And this is the tandem solar cell, whereas these are one single junction perovskite. And you can see here, they were all at 0.1, and the recent ones are lower area. So the question is this increase because they decrease the size, right? It is not the whole performance. Okay, so so far I talked to you about perovskite solar cells, and if somebody else was giving you, they will give okay, I did this kind of a treatment, that kind of a treatment, I remediated surface defects, my efficiency went up. So there are lots and lots of papers. So I'm going to switch over to another one, because the basic premises of perovskite solar cell is same, the architecture is same. There is another one I didn't talk about. They call it the inverted solar cell or PIN type solar cells. Where was this? There is something. Okay. Where in the TiO2 case, the FTO and TiO2, right? So that is the electron transport layer. So you can also reverse that combination. You can make the whole transport layer first, and then your perovskite layer, and then you can put on the top electron transport layer. And typically people use like fullerene's C60 as the electron transport layer. So that is another architecture that is slightly lower efficiency than this one, but it is very good for making flexible solar cells. They work very well for that. So now I'm going to touch on another one to tell you, although this efficiency great, people show that thousands of hours they are stable, and there is degradation processes takes place under light and thermal, heat and light. So now a lot of people like me, that's why we shifted our research focus from studying solar cell efficiencies to studying what happens when you shine the light, what causes these ones, right? So those are really challenging to find out. And this is a recent Nature review materials Osman Bakr and others have published. They analyze what happens when you have this perovskite structure, okay? A little more science here. Some of these things starts evaporating or moving out of this perovskite. Like your ammonium ion might become like ammonia. Your iodide might come out, okay? Here is HI. This is formamidium, this is methyl ammonium, okay? So this is what we focused on, mostly methyl ammonium type things. And when these guys get out, you degrade your perovskite material. So how do you measure these things, right? So one thing is you can measure the product, you can put it on your mass spec and see what kind of things are coming out. It is very low concentrations, but still you can try it. And what are the causes for it? So this is sort of a band diagram. So this is your electron transport layer, like TiO2. And here is whole transport layer, like spirometite. So when you shine the light, you do the charge separation, right? So your electrons is expected to go here, and holes have to move all the way down here. And then they call this is a depletion region. That's the sort of a driving force for electrons and holes to go in the opposite direction. But then there are vacancies, a lot of, right? So they get started, holes getting accumulated in this region. And when they get accumulated in these holes, there is oxidized form. What is a hole? It's basically without an electron, right? So in iodide, if a hole attaches, it forms an iodide radical. It loses that electron because your holes come in and neutralize it, and it's not stable. It tries to grab to another one. Typically in solution, it forms I2 minus radicals. Okay, so that's what one of the reason. And this may be a very small fraction, less than 1%, right? But when you are doing it for thousands of hours, that accumulates and that degradation contributes. And if you are doing for just 1 hour, no problem. You will not even notice it. This is only when you do large scale. So that is how they describe these different things. And we have been extensively studied, and I'm not going to talk about it now, but I briefly will tell you. If you ever want to see a halide ion movement, how the iodine moves, is what you do is you make a mixed. So basically what you do is you and iodide equal concentration, and you shine the light. And within minutes, they have these regions that are separated with bromide and iodide. How do you know it? All the emission we see shifts, absorption shifts, okay? So we can. You turn off the light, they come back to the original state. So this drew us the curiosity when we first saw the paper from McGee's group, and we said, okay, what is it causing? At least we published more than half a dozen papers, each step finding. First, we wanted to see what is the kinetics of it. So we did it. Then we wanted to see what factors control this kind of a movement. What happens, whether it comes out in solution. So those kind of things we studied, and we finally said that it's the whole extraction by iodide causes this change, because once the holes forms iodide, it start moving away from the lattice, and even it comes out into solution, okay, if you have in contact. So if you make this film, Just put it in a dichloromethane and shine light. Your solution will turn, iodine will come out. If you leave it in dark, nothing will happen. Only when light, the iodine comes out. So again, we studied the processes, and the light is the one that overcomes this entropy of mixing and trying to get segregated. Okay, there are even the cartoons on the internet says, "Are you okay? I'm just a little unstable because of my inner iodine." Okay. Okay, so again, this is sort of a perovskite perspective given by Barry Rand, which essentially supported our theme that iodide is oxidized and then oxidized iodine diffusion, and it enters thing, and most of it is regenerates, but small fraction can just get out and form this iodine vapor or this one. Okay, so that is where we stand. That's the article if you want to study how this process occurred that we published in Accounts of Materials Research. Hole trapping in halide perovskites induces phase segregation. So basically you have this electron hole transport, and because of this gradient structure, they move to this lowest iodine rich area, and that's where you start seeing the problem. So this is now, everyone agrees, is one of the problem for perovskite instability. So next thing what you do, you have to suppress that movement of iodine, right? So people are trying again, mixing so many things and other things. And one of the things, if you read any recent papers on perovskite solar cell, they say 2D, 3D perovskite interface to improve solar cell performance, okay? What they are doing is after putting these three-dimensional perovskite, they add a layer of 2D. Basically, they can add a salt of, say, butyl ammonium iodide, right? So it just exchanges here on the surface and gives you that 2D layer. Remember yesterday we talked about 2D perovskites, right? So it's the same structure. So now people claim shown to improve solar cell performance and long term. And so this is the 2D perovskite I talked about yesterday. This absorption spectrum, you can change the layer numbers. So notice that when you change from layer numbers, the absorption shift to the visible, okay? They have characteristic fingerprints for this one doing it. Again, there is various sets of done it, and these guys have even calculated the PCE improvement ratio. They say that if you have, these ones are better, whereas these ones do less than 1 means not better. So again, they have done a machine language thing to analyze the data. Okay, so again, as I said earlier, if everybody is going in one direction, sometimes somebody has to look in the other direction, right? So we just ask the question, is it really stable when it's 2D? Is it because when they do it mostly for a short time. They don't do an extended study, right? So that is the question came to our mind, and they said, let's see what happens, right? And then we saw this paper from this Aditya Moite and Kanatis, Jackie Evan, published in Science, right? The title, bilayer durable and efficient, okay? And they showed that, well, we have got this stable thing for 2,000 hours. And if you don't have it, this one. Again, all these stability curves, when you see the time scale changes to show where sometimes people put 100 hours, sometimes people put 500, because after that they start degrading, okay? Because that's why they didn't give you more time. But anyway, in this case, and they showed you this 2D layer on top of 3D layer, cross-section analysis. Again, this is a published paper, okay, in Science, very reputed journal, right? Then it is little later in Advanced Materials, there came another paper by this one, and he's from Georgia Tech. And he says, upon annealing 100 degrees, bulky cation diffuse in the perovskite layer, cause changes in the structure and crystallinity. The performance of films. If you do at room temperature, they're pretty fine, okay? This is PEAI at room temperature, There is a drop, but it's stable. But if you heat it up slightly, they start dropping down. Same systems what this guy studied, right? So this is where the problem is. How you measure the stability and clay makes a difference. If you put a solar cell, it is going to heat up, right? Okay, then there are other papers too, people showing that when you put this 2D layer, these cations diffuse in. And this one, and the light-induced processes, and they have done it and other things. So we decided to check it by two ways. One is trying to make this solar cell, and when you make solar cell, between this gold thing, there is the black grooves, we can measure the absorption changes within that film. Okay? So this will block it, but you can send your probe beam through this one and measure it. And so we can correlate under actual operation how the absorption changes. These with the 2D, we had a lower current. But for comparison, if you compare normalized efficiencies, you start seeing dropping down way quickly than this one. Okay? So that is how it is, and we can get the activation layer and things. So again, 2D perovskite can be additive or surface capping layer, better stability and efficiency at room temperature, poor stability at. So the question is why, right? So that led us, and we deposited, this is our first work we published, is we put phenethyl ammonium ion, this PbI4 layer on top of this one, and sure enough, we start seeing that wherever the 2D was absorbing, it was changing. And that is the emission of 2D. And we can take the different spectrum. You can see here it is going down with time. So that is the thing. And this is under light. Okay? Just shining light is absorption changes. And then under heat, same thing we see. We see a decrease in absorbance, decrease in emission. So your 2D layer that is there on the surface is getting mixed with rest of the 3D. It's no more staying as a 2D. Although in the beginning, in the cross-section TEM, they show nice 2D layer, it's no longer exists. So it's all diffusing in these cations, and these guys go up doing it. Okay, observe aggregate changes in 2D film, how to probe individual transformation. Still, if you want to see the individual transformation, always think simple, okay? And this is what we did. We put 3D film on one slide, 2D film on the other side. What do? You made a sandwich, right? This is cheap. Everywhere it has these binder clips to bind it. Put it on a hot plate and open it up. You can see from your eye this yellow film changing into orange. These are actual pictures. So that means the ammonium ions diffuse in here. Remember, when you go from 2D layer 1, 2, 3, 4, it shifts into the visible. That's what happened here. So here, very little change because it doesn't change. Whatever cation goes from here must change. But okay, this is what you see with the eye. How does it look from when you absorption? That's what you see in the absorption. So you see here this one going down, and this is coming up. This is the 2D, 3D combined film. And if you take out now separately, you can take separate spectrum. That's a 2D film showing that this absorption went down, but this absorption came up. That is n equal to 2. There is also n equal to 3. And all decrease in the same time. You can take emission spectrum. This was to start with 2D, and after annealing, we saw these new peaks coming up. Okay? And so this one slightly shifted because of the intercalation. So this was published in recently in Advanced Optical Materials. We try to tell you about unique properties of organic metal halide perovskites. Cation migrate across 2D interface to create a gradient structure. and need to overcome the stability issues. There are some recent papers here if you want to take a look at it. I think this concludes this talk. Any questions? Yeah, again, this is another whole field. I didn't want to dig in and bore you much, but I gave you the history of the perovskites, how we evolved, how to make a good solar cell, and then how to study the properties, right? And one of the things, current of interest is the stability. That is a major issue. So we just probed what are the problematic areas, but those needs to be addressed. Here are two thoughts. Even if they make a stable solar cell, right? You as a consumer, and I come to you, here is a photovoltaic, silicon-based photovoltaic, and here is a perovskite, and you don't know nothing about it. This is same efficiencies, same performance. Talking to the guy who runs the thing, he said there are, Germany, they opened up a production facility with 100 people working there, okay? So that much, somebody is putting lots of money. First Solar bought patents for about $80 million from a Swedish company because they wanted patents to start working. So if the First Solar can make it, it will happen. Because First Solar has a technology for thin film technology. They use cadmium sulfide and cadmium telluride based films. And it's a commercial film. Those are available. So if they can somehow incorporate these films into that one, it might work. So again, I'm not saying that it's not possible, but we have to see how to compete with the existing products too. This happens for everything, whether it's sensors or all these things. We see in the lab, we get excited, but if the companies are already manufacturing a product, they will not change just because your performance is 5% better or something little bit. It has to be transformative. Then only they will change. Because they've invested so much money to make that product. They're not going to change overnight.
Thanks. In solar cell, what is the role of spiro OMATD?
It's a whole conductor. So it's a organic whole conductor in the sense that it likes to capture whole and transports it.
Okay, which
just like a TiO2 is a good electron acceptor, and when you accumulate it, if there's one electron, it stays. If you have 10 electrons, it equilibrates with other particles. So as a result, it starts moving, diffusing. The more electrons coming in, it's like a plume coming in. It's just moving towards the other electrode. Same way, the OMITAD, it takes the holes, and the hole starts moving. It basically gets oxidized, and then it keeps on hopping and going. That's how the organic LEDs, same thing. When you connect to the wire, you need that holes and electrons go to the center and emit light, right? So that is actually, they derived from these OLEDs, this thing. There are several inorganic ones too. Copper thiocyanate, I think, is one. Copper iodide. People have tried it, but it's not as good as it. Now there is another whole conductor called PTTA. The problem is even the whole conductor is not very stable, spirometad. So we have got another work coming up. The iodine comes in and messes up your omitad. I told you that iodine gets out of this ammonium perovskite, ammonium lead halide perovskite, and that can contaminate your whole conductor because it complexes with it and it changes its whole conducting properties.
Okay. Another one thing is mention iodide ion is converted into I2. This is the oxidation of ion. When I2 is not converted into +1 or +3 iodide ion?
No, see what happens is these are solid films, right? So initially they form I dot, one I. So you need two of them to come together to give you I2. Okay, so while moving around, it bumps in and forms I2, and then that comes out. If in solution, if you are doing the same thing, you can see I3 minus because iodine and I minus, they complex. Okay? So again, this is your freshman chemistry. These are master students, right? If you put iodine in water, it's not soluble, right? But you add a little drop of iodide, everything becomes dark color and I3 minus. You know, I don't know whether you guys have seen. That was the most terrifying compound when you are a kid in school, because every school had a tincture iodine, they call it. So when you fell down in the school playing, the teacher will grab you and take a cotton and put on it, and it irritates like hell. And the way why they put it was just to burn off all the bacteria or any other things to keep it away from infection. But you might have seen this tincture iodine. I don't know whether they still use it, but I think it is out now. There are other medications. But the reason I'm saying is it forms a complex. I2 and I minus in solution forms a complex. Same thing with sulfur and sulfide. Sulfur is not soluble, but you add a little bit of sulfide, it forms S2 minus dot. So you can, it dissolves.
Okay.
So these are all complexations of these ions.
Okay.
But you can see it. If there is a solvent, then you will see I3 minus. Otherwise, just I2 will go out of the film.
We can take the interhalogen compound, the halogen having -1 oxidation state. What happens?
Yeah. What is that?
Interhalogen compounds, IF3, IF5.
I don't know about it, and I don't think anybody has tried it.
Oh, okay. Thank you.
So I don't think anybody has tried it. But there are people are trying to prevent this diffusion. See, now we know where the problem is.
Okay.
So,
Hello, sir. Which one is better to use among the layer by layer deposition or the mixed solution deposition?
again, it's your choice. Everyone who uses that method, they claim that their method is the best. Okay, so it is not proven that one method is better than the other. We always go for the easier ones and reproducible ones. So you should stick to the method that are more reproducible. Like, if you make it today, you make it tomorrow, or somebody else makes it, then it is very much nicer. So we have written procedures. Everyone follows exactly the same thing, and we try to get it.
And another thing is that the cartoon you have shown, due to iodine present, it becomes unstable. In case of certain MOFs also, the iodine modification is done in order to to make it more efficient. Actually, what is the main factor which makes iodine as a modifier in that MOFs?
Yeah, again, I showed you that the initial step is the capture of the holes. Iodine is a hole acceptor. You can oxidize I minus into I dot. So in the lattice, again, when you say we generate electron holes and hole get trapped, right? The hole doesn't get trapped. There is no the mouse to capture it. It is some kind of a chemical species. That I becomes I dot, and then it starts moving out, and then it sees another one. It forms iodine, and then boom, it starts coming out. Yeah. So again, if you use this trication like cesium and formamidium and methylammonium, it's a lot less. You can slow down that movement by orders of magnitude. So we use methylammonium because it's faster. It comes out. Yeah, do you work with perovskite? No, okay. So if anybody working, you can just try this methylammonium lead iodide film, put it in dichloromethane and shine light. You can see the iodine coming out. And without light, it will not come.
Hello, sir.
Sir,
Yeah.
I have one question. Can we develop solar cell having efficiency more than 50%?
Okay, sorry, I didn't see you. Okay. Just say it, repeat the question.
Can we develop solar cell having efficiency more than 50% using either multi-junction or single junction semiconductor?
Single junction, no, because you said there is a limit is 33%. And the closest candidate is silicon because of its band gap, and that has come up to maybe 28%. Okay, so there is a penalty to pay from the ideal behavior. In the multi-junction, basically you can control these layers that has come up, and my guess is that people have made up to about 42 to 45%, not with perovskite, but with other semiconductors. The theoretical expected here for perovskite silicon is about 38, 39%. That's the limit for this particular thing. People have already gotten 33%, and there is still room to improve. So the new thing will come. But there may be 50% possible with some other engineer design. That's how they take it to the rocket ship. These are the high multi-junction solar cells. You can look into that N-rail chart, the photovoltaic, and see what's the maximum for multi-junction.
Okay, thank you.
Okay.
Sir,
Yeah.
sir, we recycle these solar cells.
What is that?
Recycle these perovskite solar cells.
Recycling?
Yes.
Again, there are a couple of papers showing the recycle. I think there is Hang Yoon Suk from this SISF Korea. He recently published a paper in Energy Letters. He gives a way how he recycled it. But again, it's not a commercial product yet, but that's an area. If you can come up with a good recycling process, it will be a good paper. Okay? That is something to work on.
Thank you, sir.
Same thing with the batteries. There is no good method to do batteries.
Hello, good morning, sir. Actually, I come across some papers regarding whole transporting layer-free solar cells. So, I just want to ask, the whole transporting layer-free solar cell really helps to improve the solar cell performance, or is there any other reason people are working on that?
See, once you form these electron and holes, right, you saw in photocatalysis, you saw in everywhere. To get better efficiency is you have to pull them apart as soon as, otherwise they recombine. So having these electron transport and hole transport layers they helps you to, it's like putting a magnet, right? So it just goes on the other side. So that helps. So that's why, and the rate with which these are pulled, they should match. So we have done in LEDs by varying the thickness of, say, electron transport layer. And at certain thickness, you see maximum, and if you make it too thick, it drops down. So same way in solar cells, the thickness is very important of both these electron transfer, and so that their rates are matched. So a lot of times we follow the process, but the thickness of the layer is always, people don't tell you how thick they should be. But somehow it works out, and it works most of the time. But thickness is important. We showed yesterday, I didn't go in detail, when I showed you the antimony sulfide, there we varied the thickness of your antimony and showed how the diffusion of these holes in the inside system controls the efficiency.
Thank you, sir. And I have one more question, sir. People are recently working on core shell structure of different perovskite materials. Core shell technology.
Core shell.
Yeah. So it is really helpful to improve the performance of the solar cells and improve the stability and operational condition.
Again, like there are a lot of approaches have tried. When you try it, you make a bad control cell, and people compare to that bad control cell. Okay, I made an improvement from 15% to 18% by whatever core shell or by this treatment. The problem is you are not made better than the 26% cell, right? Then only it matters. So there were a lot of these plasmonic solar cells. People put gold particles in solar cells and they say, oh, we improved. It's a plasmonic effect. The problem is everyone compared with a poorly performing cell. Of course, when you do poorly performing cell, it looks better. And nobody made a compatible cell like high efficiency. Like if you want to say perovskite, you have to make at least 23, 24% cell. I'm not saying 26. That's easy to make. And now you say from 24, I made 26%. I will believe it. But if you make 15% into 18%, that improvement is not valid. The reason is it could be several other factors, not just your core shell. So that's why whenever you are comparing and claiming it better, you better have a scientific reason. And your comparison should be the right one. And this is, again, I'm not telling that you are doing it, but you see in the literature, and people submit the paper, the performance comparison. That's not a new science. Just claiming that this is better than the other one because I added this. Somebody adding something else, it's better too, right? So the thing is that, can you make the best cell and make it still to the higher one? Then only it matters. That's why if you see all these high efficiency cells, everyone has a different approach. You take from 23% onwards, somebody put it some this treatment, that treatment, it doesn't matter.
Thank you, sir.
Okay, yeah. Again, you have to repeat it.
How the shunt and series resistance can matter in the multi-layer of perovskite
The
cell.
content?
Shunt resistance and
Shunt resistance. Okay, that is more device performance thing comes in. I have not talked about it. It does play a role. And again, depends upon how well you put these layers, right? So that minimizes the shunt resistance. So in this one, it seems to be not a major problem because I have not heard anybody talking about that. In the beginning, there was some, but not. The only thing that might come is the movement of ions might make some kind of a contribution. Okay.
Good morning, sir.
Yeah.
Last question is, what is tandem solar cell and what is the major difference in tandem solar cell and other types of solar cell?
Oh, tandem solar cells. Okay. Where is it? Can you go in the beginning? Can you go in the beginning? Sorry, there is one slide there. The third or fourth slide. Okay, stop. Next. Oh, this one, yeah. Okay. So the tandem solar cell is, see here, you can make two cells. You can make one perovskite solar cell, but the problem here is your FTO is transparent, your gold is not. So what people do is they evaporate ITO on top of it. So then it is a transparent kind of electrode. So this has to be transparent so that light has to go through, right? So you can put it on the silicon solar cell. And this is called 4-terminal tandem solar cell. That means you are putting, there are 2 terminals here and 2 terminals here. So this is the easiest way to make a tandem solar cell because you are doing it. But the key thing is you cannot use gold. You have to use ITO for this one so it's transparent. So in this one, what they do is they try to grow the perovskite layer on top of silicon. Sometimes they add some layers to have it grow epitaxially. So you have to read the papers for these ones, how they do it. And there are various structures. So in this case, this is called 2-terminal because the holes generated here, they go all the way down and all the electron generated comes here or vice versa, right? So then you connect 1 terminal here, 1 terminal here, you can do it. So in this one, this is the real tandem 2-terminal because the 2 layers have to talk to each other. Here they don't have to talk to each other, they are separate. Did I answer your question?
Thank you, sir.
Yeah.
So, well,
Yeah. Fill factor tells you how good you have made the cell. Okay. Again, she was mentioning about shunt resistance. All these resistance play a part. And typically, if you get a fill factor of about 0.8, you made the best cell. If you have a fill factor of 0.5, you have to improve the design. So most of the time is internal resistance, and that's where it drops down. You waste your voltage and not delivering that into the current. So it is like an ideality factor, okay? So basically, how good is your cell, it tells. The ideal, it should be 1, and you will never get 1. But you can come close to 0.8. Yeah.
Well, I know very well that everyone wants to interact, ask questions, and get the good information.
Go to the slide where we ended.
I think Professor Delekar, we need to close this session.
No, up. Okay, here, yeah. Okay. There was another talk I planned, but I'm not going to talk details, so that's why I spent more time on this talk. But I want you to talk on this one, okay? Can I start, or you are going to say something? Yeah, this is your research opportunities.
Okay, that's all. I was thinking you are.
No, it's, I will take only 10 minutes, okay? So because I committed to talk about this, and actually I didn't prepare it, I was hoping that you guys will tell me what are the research opportunities. So that was to create a discussion points, and you can tell me, okay? We can do it, or these guys you can discuss later on. So again, research opportunities in this whole business is, you can do new material discovery, you can study properties and mechanistic insights. That's what sort of we do it. We don't develop new materials. We pick up materials developed by others and do it, and you can also try for applications, right? So it is not that one is better than the other. You need all three, right? So sometimes something you make a new material, you characterize, you study, and you also make devices. Sometimes you use the material that you have and then make devices and trying to understand. So they are all interlinked, one way or the other. You need to respect what goes on in each side or be aware of it. And okay, what are the new opportunities? Again, still people are exploring photoactive, electrocatalytic materials. We still need these things. You can engage in that. Functionalized and hybrid materials. This is another one. Okay, so that is the main theme of it, the conference, and you can basically, you are trying to bring in two different things, or you modify your particle with surfaces and do it. This one gone. Okay, we'll go with this. Again, development of new materials, established. Oh, it came back here. I'm supposed to stand here, right? I keep on forgetting. Again, you can, anytime when you, like the one I gave an example earlier, right? So we try to establish a mechanism with how iodine moves, or how does cation move. So try to understand. We are not developing any new devices. We are existing system, but we are providing that information. So this is also important. Again, you have to see where your strength is. If you are good in synthesis, go with this one. If you are in characterization, focus more, but learn this one too. That's what I do. We learn how to make materials. We don't do anybody else. Okay, let's learn it and do it. And we all make our own devices too. So you can do all three, but you can put focus on this one. Another important thing, if you are doing like photocatalysis, the back electron transfer. Very little attention is given nowadays how the product you've made reacts back with your own catalyst, right? That decreases the yield. If you can find it and optimize it, your yield will go up. Just like the forward reaction, the back reaction is also. I gave you a couple of examples how the back electron, it can be done. What you do is you add your product to a catalyst and see how the product disappears. Just like the hydrogen peroxide, right? If you put TiO2 or zinc oxide, you will see hydrogen production. But at the same time, you add excess hydrogen peroxide, it will decrease and come to the steady state. There is always, when you shine the light, there is a forward reaction, back reaction, and they sort of balance out. And that's how you see a normal yield. So this is, to me, is a one more, again, it is a old topic, but less focused. You can develop new techniques to monitor some of the changes. So that's the one. And again, as I mentioned earlier, the devices and other things. Okay, if you are working in photocatalysis, I don't have much to say, but I can tell you what not to do, right? Claim an efficiency with 3 electrode configuration. Counter electrode potential is not controlled. Just remember that fact. Okay? So don't do the mistake. You may be able to publish it, but because some of the people may not know it, but in the real world it will not stand. Claim efficiency without accounting hydrogen generated from sacrificial donor. I gave you an example yesterday. They do contribute. Same thing happened in CO2 reduction. If you're organic, make sure you do all the blanks and account for it. I'm not saying don't use it, okay? Don't get me wrong. But account for it, how much is coming from your reduction, how much is coming for oxidation. And it can be done. Another one is performance. This is a very common thing, okay? You say my photocatalyst is better than others. So this is not really a research. You don't understand anything. If you say it is better, you have to give reasons why it is. Do both things and then say what it is. As mentioned earlier, if you're electrocatalysis, your surface area could be different. Your loading can be different. The medium conditions could be different. So one medium may be better for one catalyst, other medium can be better for other ones. So there are several reasons. So find out why it is, not just saying that it is better than the others. Again, what you can try to do is based on new scientific issues along with fundamental insights. Okay, this is always a winner. If you provide new mechanistic information, it is always a winner. Hybrid functional materials with unique properties that can overcome some of the common problems. Sometimes your catalyst degrades, okay, modify it and tell if it is stable, that's it, something new. Or change the property. If you want to extend your light absorption or some other properties, can you do these things? Issues related to back electron, again, product degradation I mentioned earlier. And again, always interest, catalyst stability and demonstrate its performance and those things. Okay, this is in, again, you can keep on talking more and more. Again, when you talk about functional material, I showed you, like, we have tested, these are just a small section. We always are interested in putting two things together and see what it does, right? So either you transfer energy or transfer electrons. You can make 2D with these photoactive materials. You can add MOS2 and a silver particle and see how they So again, you can come up with your imaginative thing and study their properties. That's just to give an example. If you have perovskite solar cells or any other solar cells, you can recognize the fact that hundreds of groups are currently working in the area of perovskite solar cells. One more solar cell characterization will not make a difference. This is the reality, okay? Again, I'm not saying you should not be working on just to get to know. Again, it's easy to say, I'm working on perovskite solar cell, it's a popular field, but get your angle, what you want to do with those things. Try not to claim an efficiency improvement from, I was telling, use of any surface treatment and come with a poorly performing solar cell is not a breakthrough. Use of efficient, stable, and highly efficient in the title. This will not impress anyone. Thousands of papers have already been published with such things. And we still don't have a stable or efficient, right? And that is, it doesn't show it. That's where the number of papers claiming just efficient, stable, or highly efficient, somehow the color doesn't show up. That's the one it is been growing like crazy. Everyone uses it. Do not use a template approach. If you see most of the perovskite solar cell, they look identical, right? First you have got some absorption spectra, then you got some microscope images, then IV characteristics. some fluorescence, decay to show something, and then the stability. So they look identical. That doesn't excite anybody. So you have to bring some new ideas, new things when you are doing it. And we wrote an article called Fewer Sandwich Papers, Please. Okay? So basically what you are doing is you take this combination and vary one of them. And the article says that, just like when you make sandwiches, you have got 2 bread slices, right? That is your 2 electrodes. And then you change your, whatever you have got cheese, you have got lettuce, tomatoes, cucumbers, whatever you want, right? So same way people are doing it, arbitrarily trying something and see what sticks. That's why when you reject a paper, understand that is the reason. There are so many papers come in every day. At least I get about 4 to 5 papers on this kind of papers. Unless it stands out. If it is just another variation, it will not stand out. Just to point out why it is. So, but to read this one, he has written a nice article. It's very well read. Identify what to do. Level of curiosity. Do not be alarmed with failures. Learn to overcome challenges. Ask questions. Critically discuss published work. You will get new ideas when you try to critique. Don't take it for granted, even if it's my paper. Put it to test. Ask questions. Did I do this work or not? Like, did I tested this or not? And that's when you get new ideas. Okay, how come he missed this thing? So most of the time, we read the paper as if it is written in a stone, everything is correct. No, I pointed out, even I do mistakes. Don't get me, I'm perfect. But from the mistakes, we all can learn, right? So a lot of times, our ideas, like for example, I gave you that science paper, which said it is very stable when you put 2D and 3D. We started asking question, why didn't it show me the cross-section image after that 2,000 hours? They showed only in the beginning. What happened in between? So this kind of when you critique a paper, you will get new ideas. So again, my one message is try to criticize the work. Find out what went wrong in these papers. I know 90% is right, but there is 10%, right? Yesterday they were saying that somebody claimed more than 100% PCE. It cannot be. How did they, what wrong thing they did? So those are the kind of things. Like I know that I showed you yesterday one on multiple hole transfer. No, multiple hole transfer cannot occur. There is no evidence, right? Then you start digging in, how did they got the product? One of them is a thermal effect, which they didn't study. Probably if I study thermal effect, I can prove them wrong, but I'm not going to spend time on it. Right? So do not jump from one system to another just for the sake of publishing papers. Develop a broad theme that involves continuity in ongoing research. That's when people associate with you with credibility, right? So this is the one thing. Plan on publishing on the same topic with continuity. At least you should have, so that means the problem is good. Once you finish one project, it should result in 3 other questions. That becomes 3 other papers. So that means that project is good. When you finish a project, if you don't know what to do the next experiment, that's a dead end. That's not a great project. So we are always looking for a project that will emerge into more questions. So that is an exciting time. Like, again, I gave an example of that energy transfer, right? Okay, initially we started singlet energy transfer. I said, why not triplet? What happens if it is, both can occur? How does it compare with electron transfer? So they all this came out with questions and it's still continuing. So we can easily do another 2-3 projects before we're winding it down. So until you have, that will give you sort of credibility for that field, that you are the one expert in that field. Okay, again, always remember, think outside the box, okay? The reason is most of the time we are comfortable thinking within the box. Whatever our predecessors, senior students are doing, the junior students are following. But try to take a different path and see what happens if I change a different medium or different things, or why something is not somebody doing it. So again, that's my thing. Yeah, again, as I said earlier, you need to be looking always to the side. When everybody is looking in one direction, at least not all the time, but at least sometimes see there may be something on the other side, this one. In perovskite solar cells, you have long-term stability is still a concern. That's the one. Tandem solar cells, it is still not fully explored. Stability, ion migration, etc. is another area. Application other than solar cells and LEDs. There is a lot of people are working with, like now, the X-ray detectors and counters for scintillators. Finally, think beyond metal halide perovskite. That may be the sort of a saturating point coming up. So there may be some other materials, right? Okay, I want to thank you for all your attendance, and you guys stayed all this time and survived my lectures. It's not easy, I'll tell you, sitting here and listening. That takes a lot of courage and patience. Hopefully, you don't have to remember everything, but some of the key points I mentioned, try to remember, and I'm sure you will see a lot of success in your research. And I would like to wish you all the best in whatever things you do. And if you need any questions or things, send me an email. And as I said, I will write a short reply. And if I can't answer, I will tell you whom to contact. Okay? So that is the one. And again, thank you very much. And again, this is beautiful. It's very impressive. I don't know, whoever did it, they need extra credit. Okay?
I request all the participants to stand up and clap.
Thank you. Thank you. Thank you. I think I'm going to go now, okay? Again, you can continue. You are asking about research things. You guys can continue. Yeah.
Because of this time constraint, we need to conclude formally. Yeah. So it was a wonderful session since 16th of this month up to 19th. As in almost all lectures, Professor has summarized many things. So from the organization point of view, I must again summarize the things that Professor started with the clean energy challenge with net zero carbon. He interacted with all of us in various aspects. He delivered a nice lecture as a best teacher and excellent researcher, top researcher in the world. He talked on the nanostructures and advanced energy materials, then energy and electron transfer, solar cells. He has touched to the two-dimensional materials, hydrogen economy, then challenges and opportunities. And he also guided not only the beginners, but the doctoral students, as well as the established researchers like few of the faculty members, what to read and what to be pointed out. He insisted to read many things, but he also mentioned that whether to believe or not on certain values, for example. So this is very important because we usually make use of some of the terms. Those are not widely welcomed in the international community. So this is very important. So I must thank Professor Kamath sir from the University of Notre Dame, United States, who traveled all along, honored us to be here in the Shivaji University campus through the very small department comparatively to the rest of the world, very small laboratories, but we are producing something good. In the good journals, we are showing our presence. So thank you for delivering a series of lectures, all of which are very interactive and made it, I hope, all of us are inspired and tempted to look in the perovskite. So that was the thing actually that I personally seen. I remember when I first met Professor Kamath in Solar Forum in South Korea, where a large number of top world scientists in the solar cell, starting from Professor Kamath, Gratzel, Miyazaki, Professor Nam, Professor Subodh, myself, who I am interacted and also have the opportunity to talk with the peoples. And the same thing I enjoyed here. I personally not wasted or maybe missed a single moment of Professor Kamath since 16th of this particular. So that really, so that was wonderful thing. Because it's very difficult to be here. Sir has also mentioned that to be in the class hours together, to hear a professor and his command, to see that we shall appreciate his command to keep all of us in the exact mood what he wants to say, and to be in the involvement, to be involved in the process. So we truly appreciate your time and effort to be in our campus. I'm sure our students will remember these all 4 days. Just like, for example, Professor mentioned about the John Goodenough. I remember that he's one of the student, group student, Professor Jakyuk Kim in South Korea, who is a top grant earner in the lab. He worked in the George Goodenough's lab, and he was sitting next to my lab, my office in the South Korea. Just like that, we need to remember the things and how people are working across the globe. And it's very important that, as per my observation, many Indian origin scientists working excellent in the world, and rest of the world is looking for something better from scientists like Professor Kamath. So again, thank you, sir, for this wonderful opportunity to all of us. So,
on a personal note, I also want to, not only that, one of the memorable things is the job in the morning.
yes.
Whether it was yesterday we went at 6 o'clock. We showed up in the hotel, picked me up, we ran, then we went to the temple, and we were back very fast. I learned from it.
Yeah, inspiration from you people, so just minute to minute, and yeah. So, with the permission of the chief of this and head of the department of our department.
Ladies and gentlemen, now it's time to take a short break and recharge with some tea. Please be sure to return promptly in 15 minutes so we can continue with the insightful discussions. Thank you and enjoy your tea.
Well, we are reached to the next session of today's schedule. So we are with a distinguished scientist, a electrochemist, the top electrochemical scientist in India, who has affiliation with the top institutes in India and abroad also. He is alumni of the Indian Institute of Technology, Mumbai, top institute in India. He is alumni of the TIFR, top institute, research institute in India. And he worked with the top electrochemical scientist, Alan J. Bart, in world. He worked in the group of Alan J. Bart, you know very well, who has crossed 1,000+ papers. Coincidentally, Professor Haram has published one of the paper as an author with Alan J. Bart, which has crossed 1,000+ citations. So this is actually one of the things that I wanted to mention. Actually, in addition to his many achievements or many things we can tell, but in brief, I will like to add some more things about Professor Haram. He has worked as a postdoctoral fellow in University of Texas in the group of Professor Alan J. Bart. He is visiting professor at Würzburg University, Germany, visiting professor at University of Paris, Orsay. He is the recipient of the many awards and fellowships, starting from our Maharashtra Academy of Sciences, National Academy of Sciences. Then he has enjoyed the Boy Scouts Fellowship, then Fulbright Nehru Fellowship to work in the University of Notre Dame, where Professor Prashant Kamath is already there as professor. He has awarded with DAE Young Scientist Research Award in Basic Sciences, Golden Jubilee Research Fellowship in UDCT Mumbai, and he has also received the fellowship from TIFR to pursue doctoral research. He is a MSMC scholar. He has received MSMC scholarship from IIT Mumbai to pursue his post-graduation long time back. As far as his research schemes, or maybe as an investigator, he has completed many research projects funded by Indian agencies as well as European Commission, crossing about 3 crores of rupees. And he has a special interest in the research for electrochemical science and nanotechnology group. And as since 16th of this particular, the starting of this GIAN workshop, we are been very acquainted with the electrochemistry or importance of the electrochemistry. The Professor Haram will continue the same things and will add something more to our knowledge. So we again welcome Professor Haram in this campus, in this auditorium. Once again.
Thank you, Professor.
I request Professor Haram to continue.
Thank you, Professor. First, outside, I would like to thank Sagar, Professor Sagar Delegate, sir, for his very kind hospitality, and he kept us very good state. And thanks for the invitation. And his team also is doing hard working for this, arranging this this GIAN program. Well, already you heard. I'll just come down because for me, it's a difficulty in seeing these slides from here. Well, so you already seen or attended the elaborative classes of Professor Prashant Kamath, and after giving lecture after Prashant is complicated for me because already you have seen the sun and now we are going to see the firefly. So उनके नाम में ही PV है, so photovoltaic. So well, his main aspects, I'm following him from this Mumbai. He's also was from Mumbai, and then we are very close from quite a long time. Well, so he has created a perspective of solar cell through his spectroscopic knowledge, right? You must have heard a lot of transient spectroscopy and this lifetime and all these things. Being a perspective, because all such devices work on transfer of electrons. So obviously, the electrochemistry come into the play. So, of course, there are no selection rules like spectroscopy, but still, it has got a lot of information. So I thought I will focus more on these aspects. Okay, where the title I have chosen here is this investigation of energy harvesting system. Okay, through electrochemist perspectives. Okay, so this slide, next slide is Ghasapita slide. Everyone knows these problems of 21st century, right? So I don't want to waste my time on that. But only thing I would like to emphasize here is that these 4 circles here, which I think they will, in a nutshell, this climatic change due to our overuse of the fossil fuel or economies based on fossil fuel. You know that last 200 years worst in this scenario of Earth, about 17 lakh years of history of Homo sapien, out of which last about 75,000 years we were hunter-gatherers, and about 10,000 years we were farmer. And among all this history of Homo sapien, last 200 years were really worst. You know that. And that is because of this economical growth on the basis of fossil fuel. And then, you know, already you are facing climate change. Kolhapur must have last 3-4 years back experienced worst part of this climate change. Well, then there is a water and food scarcity. Pune is going to suffer this water scarcity this year, and then because of erratic monsoon, and then of course COVID we already faced because of this, and COVID is just a start. Okay, we are going to face many more such pandemic. So this is I'm not a pessimistic, but it's a situation for 21st century kids we are here. Well, there are a lot of discussions on international level, and then eventually our great politicians and everything decided to go for solar cell. Okay, and now all the rooftops and everywhere we start seeing such black panels. Okay, and we are push with third order. We got some solution to this problem, right? So there are solar panels now, and we are going to go for about 200 gigabyte, 300 gigabyte total power by night, about 2035, and so many plans we have, and all this Ambani, Adani, all have got now solar panels. You must have seen, right? So looks like the problem is solved, and then बदलत नाही का काय मी माझा आणू का इथे करू का so this picture is very common. This is the picture someone very senior citizen showed me near our building lift, that he asked me, sir, which field you are working on? I said, I'm trying to work on solar cell materials. So I said, why you are working still on solar cell? There are already solar cell on this Jhukki Jhopadi everywhere. So everything problem is solved now. So why you want to work on this already Ghasapita problem? Okay, and there are a lot of such pink pictures, beautiful pictures you see, where this is a part where these street lights, very remote village where there is no grid power. These pictures are very common, and we show our progress of this energy. But always bright part has always have dark side. It's like this Spider-Man. Okay, there's a dark side of the Spider-Man. Okay, everyone has the dark side. Even Spider-Man also has dark side. Okay, well, so dark side of this solar cell actually is somewhere here. This problem. Okay. The challenge with this solar cell, what we have, those are all silicon-based solar cell, the single crystal technology. Okay, you know that there's big ingot, and from which we cut the wafers, and we stick that wafers like papad on these panels, right? Black panels. Must have seen, no? There are circle everywhere. And now challenge here is that they are all indirect bandgap semiconductor. They are not efficient system for solar cell. Though they are very good for transistor, they are not good for solar cell. Okay, because we have choices of direct bandgap semiconductors. Okay, and this we are using basically technology which is extended from semiconductor technology used in making transistors. Okay, and because of which, and not only that, these high temperatures techniques, we have to grow single crystal, okay, high energy incentive technology, you have to spend a lot of energy to make those ingots. And once you make the solar cell, energy, after spending so much of energy, another challenge is to get that energy back. Once you spend some energy, you have to get this energy back. That takes almost about 5 to 6, 7 years, depends. So after that, you start getting dividend. Okay, dividend of there's a dividend basically. So dividend will come after 7, 8 years. So till then you have to wait. So that is called payback time. So we want solar cell which can be made out of direct bandgap material, which is cheap, chemically processable, because physical processes are always energy incentive. Chemical processes relatively happens at low temperature. Okay, so we want to develop materials which can be formed at low temperature, less energy will be spent, and payback time will be around 2 to 3 years. That's the ideal thing actually. Well, so, but it's difficult because we are expecting the Purushottam. Okay, all the properties in one person is difficult. So, well, with all this dark side and bright side, we have to move on. Okay, is it not? So, there are a lot of choices we have right now. If you are chosen to go for such a direct bandgap semiconductor, okay, there are cadmium tellurides, cadmium indium diselenides, there are copper zinc tin sulfide, okay, then there are lead sulfides, and there are, you know, that this perovskite you must discuss in last lectures. So many materials are there which are available, disposal to us which are very efficient. Okay, direct band gap semiconductor. But then question is, why we are not making the solar cell out of this? Okay, this problem is known, solutions are known, but still we are struggling for last 50-60 years to make the solar cell. Okay, I think Prashant must have discussed all these problems, stability of solar cell. I'm not going to go that side, but advantage of this material are many. First advantage is that we can coat that solar cell or panels on the flexible surface. So I can have solar cell on my back or backpack. Silicon is very brittle material. It's a wafers. We have to stick to the very rigid panel. Here we don't need to do that. We can have basically solar cell on the backpack, on a cap. You must have seen the Chinese cap with fan on the top. Huh? This is amorphous solar cell actually. Okay. Well, so they are more cheap. These are amorphous solar cell actually. It's technology where they are very cheap, very, very cheap. Well, another important advantage of these materials, we can form a quantum dots. Okay, which silicon is not possible. We will not discuss that now, why silicon cannot form quantum dots, but we can form a quantum dots. Quantum dot means what? We have a nanoparticle which property can be tuned or tailored with the size. And it has got great advantage basically. Now we have a handle to change the physical property of material without changing the chemical property. Same chemical property, but different physical property. Okay, some of you must have read about it, some of you must have learned last lecture, but quantum dots basically, they are very important material they are seen as a very futuristic material for solar cell application. So I have decided to talk about quantum dots today, and I will just give a very nut bolt of quantum dots, little bit here and there, and then I will talk about this, what will happen. We will try to do electrochemistry with quantum dots, what information we get, which is important to develop the solar cell. Okay, so my whole talk is revolving around how electrochemistry can be used to analyze the material, futuristic material for solar cell, third generation solar cell. Okay, I think you must have discussed first generation, second generation, third generation. Okay, first generation means silicon, second generation means thin film, is it not? And third generation basically are solution based solar cells. So we are sometimes it's called chemist solar cell, we call it. Well, so I don't have to put these photographs here. You know already, you must have read it. Who got Nobel Prize? Okay, 3 guys got Nobel Prize. Bavendi, Bruce and Ikimo. This is all now in US. This is Russian. This is basically Americans, and this is from, I think he's basically from Italy. So all 3 guys won Nobel Prize for quantum dots. Quantum dots are known basically for so many 50 years. Physicists know quantum dots. They have done a lot of experiments with quantum dots. In chemists knows quantum dots. They call it as this divided particle or collides. Even Michael Faraday knows the divided particle about 250 years back. So it is not new. But what is new to get this Nobel Prize? Okay, what's new in that? The novelty of this is basically to develop the synthetic methodology to make those quantum dots with controlled size called monodisperse particle in kilograms. Physicists used to use quantum dots, but only 1 or 2 quantum dots lying on the substrate. But now Bavendi has made or suggested a methodology called hot injection method, by which some of you must have using hot injection method for making quantum dots. Okay, so one can make now the quantum dots in kilogram, and very college lab scale actually. Now these experiments are introduced to our MSc student. They make quantum dots and do all these other parts. So that means he brought that technology into the level of college. Anyone can cook these quantum dots in large scale. And second part basically is this guy, this Louis Bruce, very quantum dots called effective mass approximation. We'll discuss after some time that part. Okay, so what are the contribution of this Nobel Prize winners? One developed the chemist way to make those quantum dots, and second person developed basically the theory, very simple theory to explain the property of size dependent property of the quantum dots. Well, so in my perspective, all three this Ikimo basically is actually started with quantum dots idea. He prepared tinted glass of quantum dots of copper chlorides. Okay, tinted glasses. Well, so I will not go into detail of their work, but in my perspective, their contribution is actually to develop chemist perspective. Okay, for quantum dots. Physicist was knowing the quantum dots, but he has developed chemist. He has brought this whole idea of quantum dot towards the chemist. And chemists now become very active in making those. And because of those activity, we could able to develop third generation solar cell. Okay. Well, so I think these pictures are redundant basically, how property of matter change with size. For example, in this example, the cadmium sulfide, which is yellow in color, become pale yellow when you restrict the size up to 4.5 nanometer, and 3.9 become chalky white. Means what? Chemically, it is cadmium sulfide, but physically, they look completely different, physical appearance. And change in optical property means what? Change in electronic property, because optical property is because of electronic transitions, right, which happens in UV visible region. So change in optical property means what? It is because of change in electronic properties of the material. Then another example of cadmium selenide quantum dots here. It gives beautiful colors. Chemically, all 5 bottles are cadmium selenide, but they start giving some different colors, different luminescence. Okay, so very difficult to comprehend that all are got cadmium selenide. Beauty of it, just restricting the size. Well, this particular effects basically is shown by strongly bound solid. Means what? Who has got covalently bonded solid. Okay, if you expect to give this property by chalk calcium carbonate, okay, if I break the chalk into 2 pieces and ask questions whether this piece is property of this piece is equal to this piece, you will say yes. Even if you down to 1 calcium carbonate, you go to the same property, but that is actually molecular solid. 2 calcium carbonate molecules are bound to each other due to van der Waals interaction, not because of covalent bond. The materials which has got covalent bond like diamond, cadmium sulfide, cadmium selenides, all these chalcogenides, okay, those materials start showing this property in somewhere in nano size region, below particular size. Okay, we are going to see why below particular size. Okay, and that effect of change in property with size is called size quantization effect or quantum size effect. And those nanoparticles are called quantum dots. Means what? All quantum dots are nanoparticles, but all nanoparticles are not quantum dots. Always remember this. Some nanoparticles start showing this property and they are quantum dots. So you can't prepare quantum dots of carbon, for example. It's very controversial to make quantum dots of carbon. Okay, so there is a fashionable to make these carbon dots and do a lot of research actually. But myself, if you I'm a hardcore physicist, chemist, you can call anything to me. But then I will not agree with that. Okay, so it is been shown by strongly bound solid. Well, I think I emphasize enough for this. Let's understand chemist perspective. Chemist knows MO theory. In BSc days, we learn about molecular orbital theory, carbon monoxide molecule, nitrogen molecule, is it not? Oxygen molecule, and we explain why oxygen is paramagnetic, is it not? Well, oxygen is paramagnetic shown actually by Michael Faraday. Very simple experiments. I'm not going to discuss this right now. I'll divert from that. Well, so you know that when the bond forms, there will be when 2 sp3 hybridize. I have not shown here another one. 2 sp is for silicon, and 2 sp3 hybridized orbitals, when they combine, you know that formation of bonding orbital and antibonding orbital. You learned this. It's not. That means I got now silicon 2 entity, like O2 entity, like N2 entity, like carbon monoxide entity. Okay, biatomic. Well, if I add more such atoms, okay, like 5 atoms, obviously I will get 5 bonding orbitals, 5 antibonding orbital, and there's a gap. Okay, if I still reduce, काय होते? माझं जोडू का? माझ्याकडे आहे, जोडू का? Thank you. Well, sorry for this interruption. So if I keep on adding these atomic orbitals, okay, LCAO, linear combination of atomic orbitals, I get this molecular orbitals here. Okay, number of orbital divided upon number of atomic orbital. If I keep on adding more, just give it to me. I will connect my own. करतोय ना मी, दूर गेलं की नाही असं होतं. मी करू काढतो तुझं. फक्त मला परत दे. Yeah, I'm good. Sorry. Well, so I keep on adding this. काय होते? एक काम कर ना, लॅपटॉप मागे लपतोय पण याला इथे चिमण्या शॅडो येतो. Well, so if I keep on adding this atomic orbital, I get this molecular orbitals like this. You can see this initially these orbitals were discrete, but now when adding more and more atoms, they are getting fused to each other. They are very merging to each other. Okay, at the end of the day, they become completely continuum. Okay, what we get? Valence band, conduction band, and there is a valence band edge, conduction band edge for bulk. And we know the semiconductor property. We all learn in your BSc days. But suppose if I happen to freeze this growth somewhere here, then what will happen? Now my orbitals are not anymore continuous. They are discrete. And you know this kind of property of molecular orbitals are from the molecular solid, not from solid like silicon. Okay. Well, so what if you try to freeze the size somewhere here? I can now define this whole structure by HOMO means what? Highest occupied molecular orbital, lowest occupied molecular orbitals, and you can see the gap between this HOMO and LUMO start decreasing with size. Okay, here at this side, if a size increases, the gap decreases, or size decreases, the gap increases. Okay, so if we try to freeze our whole growth here, the solid which is otherwise has got very strong property of solid, they start showing molecular properties. Okay, and that particular phase is called quantum dots. And this happens when the particle size is about in nanometer. Each semiconductor has different sizes. We're going to see why each semiconductor has different sizes. Okay, well, so this is our chemist perspective. Let us touch to physicist perspective. Okay, how physicists look at this problem. Here, this is the theory actually developed by Elie Bruce. I thought I should tell you in a nutshell what the theory is about. Well, when this again the semiconductor, there is a valence band edge, conduction band edge, okay, and there is a band gap. If I provide the energy to the semiconductor by thermal energy or by light, what will happen then? There will be formation of electron hole pair. We know that. And the electron hole pair, they are oppositely charged. They start interacting and form quasi particle. It is called exciton. They spend more energy with each other. Okay, and it has got lifetime at steady state. So it has got some lifetime. There are evidences they are together. There are spectroscopic evidence they are together, and it is called exciton. It's like you can view this problem as a hydrogen-like system. Positively charged nucleus and negatively charged electron. We teach to MSc students, right? Hydrogen-like systems. Is it not? In quantum chemistry. So basically we have now exciton. Okay. And once I define the system, I can write the Hamiltonian. You know that. You learn this quantum chemistry. Okay. In Hamiltonian, I have got kinetic term. I have got this kinetic term for electrons, for holes, and there is a potential energy, Coulombic interaction. I can write such terms very easily. Now I can do some approximation. I can now write the Schrodinger equation eigenvalue equation, and I'll get eigenvalue, right? We did our MSc days. So now problem now boiled down to two particles in spherical box. What are two particles? Electrons, holes, and what is my spherical box? Nanoparticle. So their motions are restricted inside that nanoparticle. Okay, and now can solve the Schrodinger equation and I get the solution. Again, I got kinetic term and potential energy term. Well, don't worry about mathematics. I'm not going to go beyond this mathematics. Well, so now we have got solution. A typical physical chemist bad habit. Once they get solution for differential equation, they start seeing the limits. What will happen to this limit? What will happen to that limit? What will happen when R is small? What will happen when R is large? What is R? Diameter of the box. My box is spherical, not the one-dimensional box we learned in your MSc days. Okay, with infinite energy. Remember this? 1D box problem in quantum chemistry? What it represents? It represents the translation motion of the charged particle. Well, so we have this system now. This actually very simple theory developed by L.E. Bruce for quantum dots. Well, let us see the extremes. What are my extremes now? When R is large. When R is large, the box is big, R square is still large. And reciprocal of R square is negligible, 0. Is it not? So first this term become negligible and my energy is actually dictated by 1.8 electron E square upon epsilon R. Epsilon basically dielectric constant. So what will happen now here? Now if you work it out back to another calculation, what we're going to energy is about 0.01 electron volt. Very small energy. So exciton has energy of togetherness is 0.01 electron volt. And how small it is? If you consider kT is the energy available at room temperature, which is about 0.0256 electron volt, that means this kT is double than this energy. So energy available at room temperature is sufficient enough to excite the exciton. And what will happen now? These excitonic bands are just lying below the conduction band edge because of this small energy of 0.01 electron volt. And even at room temperature, it is so close that all the electrons basically actually are occupying this conduction band edge. We learned that actually. Is it not? So that's why they become free. They become free means what? They become free means they are not bound. Where they bind? To nucleus. So they are free electrons. They have no as a restriction. The energies are not quantized. That means I can treat that electron as a gas, classical gas. You know that physics we do that. So I can apply all the classical theory of kinetic theory of gas to this problem. I have not go that side, but well, so I have got now free electrons in the conduction band which are available for conduction. We learned this part in your MSc days. Well, so it is situation is like a free bird. It can go anywhere. The bird can cross the India-Pakistan border. You don't need visa for that, right? Anywhere they can fly. Is it not? Well, so but now I had to check another extreme. When R is small, when my box is small, then what will happen? Now here somewhere R is still big in centimeter perhaps. Still my exciton can go anywhere in the particle. Exciton is very small, size in nanometer or Armstrong. Box is 1 centimeter, means for them it is of infinite size. Okay, like I can go, I can move only in Maharashtra. I can't cross Maharashtra border. That's fine. Still I have got a lot of freedom. Okay, is it not? A lot of freedom. But now is next situation. Suppose I have been asked to just remain in Kolhapur, in hotel, and you can't leave the hotel. Then what will happen? Then I have got a restricted movement. Is it not? I have got my degree of freedom is less. Where did you use the word degree of freedom in physical chemistry? Remember this word, degree of freedom? There are modes. There are modes. The molecule can store the energy in the modes. What are the modes? translational, vibrational, rotation. You learn this, you know already. So there are modes. Now I have got less degree of freedom. I can go to bathroom, or I can go to bed, or I can just peep out the window. Enough. So my degree is restricted. Well, so suppose I have been now restricted in a telephone booth. Young generation have not seen the telephone booth. Our generation go to for this PCO and calling someone on this common phone, and you have got mobile. So if suppose you have been basically asked to stay in the telephone booth, that means what? How many degree of freedoms you have? Very few. Is it not? Now this exciton has got already, heartbeat is already up. Okay, and is excited now. And he has already has higher energy states. I am restless now. Okay, and now it's last phase. I have been dumb in the dicky of our car, trunk of car. I can't move. Imagine करो, मला पेट्यावरच बंद करून टाकलं. This is the situation. So now this guy cannot move at all. So now my size of exciton is comparable to that of box. Now I have got very, very small restricted degree of freedom. Okay, I can occupy this quantum state or this quantum state or this quantum state. Instead of continuum, I can go anywhere. Now I have got very restricted mode of motion. And at this situation now, my size of exciton is decided by size of particle. And from that point, where size quantization effect start coming into the play. Now that is the critical size below which particles start showing completely different property. Okay, which is called size quantization effect. Why? Because particle has restricted modes. Its energy is quantized. That's why it's called quantum size effect. Size is quantized. Okay, well, so it is called confinement of charge in the small space. To be more accurate, it's confined. Charges are confined in a small space, size of exciton. Well, so at that situation, what will happen is that below that size, critical size, I already discussed this. All these things we already discussed this part. Now, initially my birds were free. I'm a free bird, and now I have been in small cage. Okay, and situation can very well describe. Okay, I will ask some students are there. I think this looks like student, so I can ask someone to open this box. Ughada, patkan ughada. What happened? There's a snake in the box. She got a little bit psyched. Anyway, so actually this is exciton. And I am now pushing this exciton into confining into that small box. Okay, so energy is high. How do I know energy is high? It immediately pop out. Is it not? So you can imagine now exactly same thing happened to exciton. This is electron, this is hole. Okay, and is in small box. And this size quantization effect. Just to my son's model, which I purchased about 25 years back. Still I am using it. Shivaji's son, Shivaji is my student actually. Yeah, he's my student. Yeah. Well, so this is size quantization effect, and that's exactly Louis Bruce basically described. Very simple, convincing theory, and just not important theory is convincing. You should be able to calculate. It should work. If your theory doesn't work, it will become just hallucinations. Okay, diva swapna म्हणतो मराठीत. असं no use. Okay, they convert into reality. Well, so what will happen now here? Now, this is a situation I have put it here. This is the blue one is the situation where there is a semiconductor solid, and when you start putting the restrictions, your band starts shifting towards the blue side in the spectrum, and your peak become very sharp. Is it not? Well, so in nutshell, in corollary, basically, in Nobel Prize, if you go to the site of Nobel Prize, this is what the picture is given. This whole picture is given. In short, they have explained what is quantum size effect. Okay, you can see here, particle size decreases, the blue shift from red to blue. Particles start showing different colors from red, longer wavelength, to blue, shorter wavelength. And you can see the electronic wave functions are now getting more and more restricted, crumble inside this particle. Here basically, if you, the application is that if you put on the blue, this same chemicals start glowing a different color. Okay, that's what we see here, right? Last time we have seen same cadmium selenide start showing different color. Well, this story, this is the experimental of various semiconductors, cadmium selenide, cadmium telluride, all the semiconductors are important for solar cell application because they have got very high absorptivity. They absorb more light per gram. And you can see as size changes from about 8 nanometer to about 1.85 nanometer, there's a blue shift in the spectrum. You can see in all the cases, 5.7 to 2.3, and here in this case, 8.4 to 2.5. You can see the blue shift in the spectrum, immediately evidented from this. This theory has got a lot of image support for. Well, so, and all this property, okay, has basically is holy cow in development of solar cell. And this picture, I think Prashant must have shared with you. Okay, it's a rainbow solar cell where now in case of dye sensitized solar cell, what happens? Dye is not stable. Okay, dye start degrading because of photo degradation. When you expose dye to, even when you try to keep your cloth outside the sun, they become fed up, right? Any dye starts fading up. Is it not? So dye has got undergo photo degradation. But we need some material we don't want photo degradation. Semiconductor quantum computers are quite stable in that situation. Not only that, they have got very high absorptivity. They absorb more light per gram. So obviously it's going to be very important material for a solar cell application. And people have developed this solar, last 20 years they have developed solar cell by, it's called quantum dot sensitized solar cell. Instead of dye, people are using quantum dots. A lot of new ideas. It was not new really, but I'm telling you. Well, so now there are a lot of other ideas like, now I can change the size and I can have a rainbow type situation. So now I have got heterojunctions of various sizes of same semiconductor, let's say cadmium selenide, and I can now coat one above other so that they will absorb all the light like this, and they can increase the efficiency. Since they absorb all the lights, whole spectrum, okay, it will basically expect to be more efficient. Well, these are ideas. That means we are bringing two kinds of semiconductor together, right, to form a heterojunction. Well, when you do that, what will happen now here, the situation? You know this guy? This is a vacuum layer actually. It's called local vacuum. Physicists call local vacuum. Means that particles have no interaction. I can say the Swarga mana, Narak mana, Kai mana. Okay. Here in this case, basically there is no interaction. Particle has free. Okay, soul is free. Okay. And then when you, normally the energies of those states are measured from the vacuum. Physicists measure all energy from the vacuum level. So these are the vacuum level, okay, and there are basically semiconductor, the wider band of semiconductor. This is valence band edge, this is conduction band edge, it is narrow band of semiconductor, valence band edge and conduction band edge. The energies, chemist measure, electrochemist measure energies in NHE, normal hydrogen electrode. Physicists measure energy in with respect to vacuum. Different scales. Well, so this is basically ionization potential. We call valence band edge. Some people call ionization potential. Some physicists call. And there is a electron affinity here. EM is electron affinity. All this term you learned actually. Well, when you try to combine these two semiconductor of different band, what will happen now? We form heterojunctions. But now, without changing this band gap, suppose if I have different semiconductor to arrange, I have many possibilities, many choices I have with me. So I can have my I can choose semiconductor I can place over here, or I can choose semiconductor I can place over here. Okay, Now challenge here is that now, your whole challenge here is by using UV visible spectroscopy, I can determine the band gap. That is very easy. But my challenge here, I can't measure the valence band age and conduction band age with respect to vacuum by UV visible. Okay, if I put my semiconductor somewhere here, if I put my semiconductor somewhere here or somewhere here, it has got different effects basically. They will have different junction properties. So we must know, before forming such heterojunctions, we must know the valence band age and conduction band age of the semiconductor material with respect to vacuum. And our UV visual spectroscopy will never give this information. So we cannot design such heterojunctions, such efficient heterojunctions, okay, without knowing their valence band age and conduction band ages. Now, this is a problem statement now for solar cell. This is a problem statement, and we have to solve this problem now. Okay, so there are physicist way to estimate this valence band age and conduction band age. One of the way physicists do is by photoelectron spectroscopy or XPS, X-ray photoelectron spectroscopy. Sometimes they use also UV photoelectron spectroscopy for semiconductors. So by which I can determine the conduction band age, and by using UV visible, combining that information with UV visible, I can estimate the, by XPS I can determine the valence band age, and by using this UV visible I can estimate the conduction band age indirectly. That's what people are doing. Another way of doing it basically is scanning tunneling spectroscopy, by tunneling effect. So here what we do, we hold the single quantum dots on the substrate. See, once you try to put single quantum dots on the substrate, it will not remain there. Okay, they will be Brownian motion, they will move here and there. So to reduce that motion, you have to decrease the temperature to liquid helium. So they will has tendency to stay at one place. And then you can bring this tungsten tip and measure the energies by tunneling spectroscopy. It's a very difficult experiment. People need about 15 years, 20 years of training to do this experiment. It's very difficult. Very specialized group in all over the world, they can do such experiments. So both the techniques are not available for chemists, poor chemists like us. So suppose I have to design the solar cell. I don't know valence band conduction band. I'll go to some physics department. बाबा इसका एक्सप्रेस कर दे दो, वो 6 महीने लगाएगा. सर आज वैक्यूम नहीं आया, सर मेरा कुछ उसका ग्राउंड लीक है. Is it not? So many things will be he will tell. And he's not lying actually. This problem with any machine operating at ultra high vacuum, 10 to minus 9 torque, there are inherent problems. Okay, अपने लाइट स्टेबल नहीं होती है. वैक्यूम आ जाएगा और सडनली भप करके लाइट चला जाएगा. So क्या फिर पूरा का पूरा एक्सपेरिमेंट go to vain. So there are many practical challenges too. So shall we stop for this? The guy smiling, they must be experiencing all these problems. See, well, I'm also a student of chemistry. Don't worry about that. Okay, don't worry about that. So what you do? You transfer electrons like these two techniques, 2 phases, right? Like I have shown here. What is electrochemistry? When you ask the question to just freshly appear students based on your classrooms, MSc, they will say chemical energy can be converted into electrical energy and so on. Is it not? Our typical printed textbooks, printed notes, Himali, Manali, is it not? So definition is given in those so-called textbooks. Well, so electrochemistry is completely different. If you go for very beneath, it is basically a charge transfer, electron transfer between 2 phases, 2 conducting phases, 1 conducting phase where majority of charge carriers are electrons or holes. That phase is called electrode, and another phase phase means thermodynamic phase. Remember, when I used word phase, the thermodynamics come to the play. System, phase, surrounding, all are our known terms within chemistry. So I have another phase, okay, another phase which is maybe liquid, maybe solid, but the majority of charge carriers are are ions. So electrochemistry dealt with transfer of charge between electrode and electrolyte. One is electronic conductor, other was ionic conductor. Well, so when this happens, obviously my thermodynamics and kinetics instinct comes into the play here. When it happens, obviously there will be a driving force. Chemist major driving force in terms of free energy change, delta G. So here in this case, to have spontaneous transfer, delta G should be negative. Okay, so it's spontaneously transferring, and there is when charge is transferred, when chemical reaction occur, you know that pass through some barrier. Is it not? This is basically activation complex theory defined like this, right? And there is a barrier. So when this charge transfer takes place, it's very interesting to know the thermodynamics and kinetics of charge transfer, because once I understand those properties, then I can design very good solar cell, I can design field impedance spectroscopy. Okay, I have rotating disc electrodes. Some of you must be doing some ORR, HER reactions, right? So the disc actual electrode is not stationary, it is rotating with known RPM. Well, it is called hydrodynamic technique. So we can control the mass transfer very easily and determine the kinetics parameters. We will not go into that more detail. And there is a cyclic voltammetry. If I do a very fast scan, I got fast scan cyclic voltammetry where I fill orbitals. Is it not? When you try to give the electron toward the solution side, there must be someone to accept it, right? Without that, nothing will happen. Well, this situation is depicted over here. I have electrode, this whole rectangle assumes electrode, and this is electrolyte. And these are redox orbitals. Maybe K3P6, K4P6. Okay. There are seric serous, ferric ferrous, stenic stenous. There's so many choices I have for redox in inorganic ions. Well, what will happen in this whole thing? I have another electrode and it's a battery, a power source. I have a negative terminal and positive terminal. Okay, and when you polarize this electrode by negative bias, then means what? I am pushing electron in the electrode. Is it not? I am pouring water in the well. So what will happen to level of water in the well? It will start rising. This depicts basically the metal based on what? Band theory. There is a empty bands and field bands, and there is a Fermi level here. Remember this? Metal description of metals with band theory. Semiconductor we have seen, right? There is a conduction band, valence band, and band gap. Metal, how to describe metal? There is a half filled conduction band, and where you get basically Fermi level. We learned, right? BSc we learned all these things. So what will happen now? This is energy axis. If I apply negative bias to the electrode, what will happen? I am pouring electron in the electrode. So what will happen now? My orbital start filling. They are filling. I am increasing negative energy, increasing this energy to the electrode, and now energy of electrons in the electrode is higher, just higher than the empty orbitals in the solution. So electrons see less energy that side. So obviously they have tendency to go towards less energy. So they will spontaneously transfer from electrode to electrolyte. When I say spontaneously, mean delta G is negative. You remember this as a chemist, you know. When spontaneity means delta G is negative. So they will transfer from electrode to the orbitals, and the passage of current will be there. Current will flow from electrode to electrolyte, and that current is called cathodic current. Okay. Exactly converse way, I can now I can pump out the electron by applying positive bias or less negative bias. What will happen now? The electron will not start jumping from solution to electrode, and opposite current will flow. It is called anodic current. So I have cathodic current, I have anodic current. Cathodic current normally undergo reduction in the solution side, and anodic current normally undergo oxidation at solution side. Well, with this very vitamin tablet of electrochemistry, we'll proceed now. Okay, another tutorial picture. Here basically, in this I have shown here how potential is changing with time. Okay, more negative, less positive, more positive, less positive. Okay, positive negative has no meaning in electrochemistry actually. There is nothing like positive actually. Only there is negative, that is electrons. Less negative or more negative. Positive is only for our notion, because we are human being developed as a positivity, negativity, right? That okay. Negative. वाम बोलते ना, वाम हस्त. बुरे काम डाव्या हाताची देण म्हणतो ना आपण ते. Well, so our negative positivity very completely relative. A lot of cultural aspects are there in this, but here nothing like negative here, nothing like positive here. All is negative electrons only, whether more electron or less electron. So very relative. Well, so when I try to reduce the potential from point A to point 2, what will happen now? Linearly with time. Okay, if I don't choose it is called linear strip voltammetry. If I go and come back, it is called cyclic voltammetry. We learned this, right? Well, here in this illustration, I have shown the solution, platinum electrode, battery, and rheostat. Circuit is complete. Okay, now I am moving this rheostat so that I am applying more potential or less potential. Okay, now what will happen now? That I am changing potential with time. There is a redox inside that solution. I think visibility is not there, and positive down. Okay, well, don't worry about that. Now I am applying potential now. When I apply potential, what will happen now? Here, see the change here, the color, density. What will happen? My ferric ions are getting reduced to ferrous. That means the concentration of ferric ions is less near the interface. Agree? Current is flowing now. It is you can see current is now flowing. Initially it was 0, a little bit to rising side. Now I am applying more negative potential. Okay, and more. See, you can see as I apply more and more negative bias, my current start rising. Cathodic current start rising because of reduction of ferric to ferrous. Well, so if I still increase this, current state increase. What will happen next now? If I apply more negative bias, current will still increase or decrease? It will in fact decrease. Why? Because formation of depletion layer here. Mean once all this ferric ion get reduced into ferrous, there is no ferric ion present near the solution, near the interface. So though electrode is in position to transfer the electron, there are no acceptors in the solution side, because they are already converted into ferrous. So what will happen to current? Current will start decreasing. And then if I reverse the okay, I think it's responded. If you reverse the potential from here to down, the ferrous ions present near the interface get oxidized back into ferrous. So we get complementary peak here of same size. If we measure number of coulombs in this peak, will be exactly identical number of peaks here. This is called reversible electron transfer. Okay, if I give 1,000 rupees to Shivaji, okay, and on the weekend Friday, and Monday I demand that money. Shivaji could able to give me the 1,000 rupees back, my electron transfer is reversible. Okay, but suppose Shivaji spend that money at the weekend, what will happen now? I am not going to 1,000 rupees back, I will get 500 rupees back. That means electron transfer followed by chemical reaction. And that process is called quasi-reversible or irreversible. If he refused to give me money, then it is completely irreversible. Okay, number of coulombs if we measure here, we get it all coulomb back. That means the process is reversible. This is reversible cyclic voltammogram. And there are very interesting part is there. I can now measure basically here the standard redox potential of ferric pairs. So means what? This whole simple cyclic voltammogram has got thermodynamic information of electronic states. I got thermodynamic information of electronic states. Simple cyclic voltammogram in the solution, just bigger. Well, so we'll extend this idea further. We're going to discuss a lot of ideas actually. Before I come to my last part of is very small, but I will develop whole tutorial into the ideas. Well, now I got pentylene molecule, which is organic molecule. It's an aromatic system. You know, we have learned Huckel theory. Is it not? There is a bonding orbital, there are anti-bonding orbitals. Remember this, and the HOMO and LUMO as shown here. By MO theory. Now, if I apply negative bias to this pentylene molecule, okay, what will happen now? I apply more negative bias, what will happen now? The electron will transfer where? Where are the accepting orbitals? Anti-bonding orbitals. And where electron will transfer first? In lowest unoccupied molecular orbital. So, this current flow is due to transfer of electron from electrode to LUMO. So this potential I can mark LUMO of this molecule. My electron transfer is reversible one. After getting electrons, that pentylene molecule doesn't undergo any chemical reaction. So if I reverse the bias, direction of potential, what will happen? My all radical, that is here pentylene anion radical, will get back into neutral molecule, okay, and I get complementary anodic. This is a cathodic peak and complementary anodic peak. Any doubt? Well, if I apply positive bias, opposite side, then now I am going towards the positive side. Means what? I am snatching the electrons from the where? Highest occupied molecular orbital, HOMO. So now I can mark this position as HOMO. Again, my electron transfer is reversible one. I get complementary cathodic peak. So whole voltammogram consists of first part is cathodic by complementary anodic peak and anodic peak followed by complementary cathodic peak. And now, beauty of this experiment is I can immediately estimate HOMO and LUMO, which otherwise I need what? UPS. And tons of data is available. All these inorganic chemist formation of complexes, they determine HOMO, LUMO by this method only. And it's backed by theory. Okay, it's a well accepted fact. So cyclotherapy can be used to determine the HOMO and LUMO of the aromatic system. Okay, well, so this is another molecule, you know, Buckminster fullerene. This guy basically can accept 6 electrons, 1, 2, 3, 4, 5, 6, reversible. So even you put 6 electron for radical is unstable, as you have learned this. You want to put 6 electrons, still it is stable, and we can get this electron back step by step. So by cyclic voltammetry, again we can verify this number of states in C60 molecule, C70 molecules, all organic molecules. We can study this. We can judge what? We can judge the orbitals present in the molecule by cyclic voltammetry. Okay, I'm telling you the physical chemist telling you all these things because normally these techniques are used by analytical chemists to estimation. Okay. Now I am telling you, we are now studying some physical chemistry out of cyclohydrometry. Well, we have our system now. We have quantum dots. Already we have seen quantum dots has got HOMO and LUMO. Okay. Suppose I prepare dispersion of quantum dots and do exactly same electrochemistry, cyclic voltammetry with this quantum dots. So what do you expect? If my electron transfer is reversible one, I will get this kind of cyclohydrogram, and this peak I can mark LUMO, and this peak I can mark HOMO. Agree? Exactly like pentylene molecule. But suppose my electron transfer is not reversible one, that means what? If I transfer the electron to the quantum dots, it will undergo chemical reaction. So when I reverse the bias, I can't get that electron back into the electrode. That means I'll get irreversible system like this. But still I can mark HOMO and LUMO. And I'll get some extra peak because once it undergo chemical transformation, that chemical transformation, the product also will become redox active and start showing some peaks, small peaks. Okay, so if my electron transfer conduct is reversible one, I will get this kind of response. If it is irreversible one, I will get this kind of response. Okay, so with this hypothesis, we did the experiment long back, 22 years back. And then we found that the way we thought of, we got cyclohydrogram. This is for quantum dots of cadmium sulfide. Okay, here this green line is a baseline. If there is no cadmium sulfide quantum dots, you get this baseline. And once you add cadmium sulfide quantum dots in the solution, you get this kind of response. Okay, this is C1 and this is A1. C1 means this is cathodic peak and anodic peak. This is from this peak we marked the LUMO, and from this far peak we mark HOMO. And it matched extremely well with the spectroscopic data. In fact, when we did the experiments, I wanted to publish in JACS when I got the results. So I went to Alan Bird, my mentor that time, postdoctoral mentor. He was a chief editor of JACS. JACS office was there opposite to my lab. He was sitting there. I went there, and Baba was a publish karna hai JACS. Obviously, all these biologists got aspiration to publish in JACS. So immediately, no, I can't publish. He said, if I publish, I will be biased person. Already I am a chief editor, I am your mentor. So people will then start blaming me. This guy is accepting his own student's paper and publish in JACS. Okay, so he said, I can't do it, but I can give a solution for this problem. This weekend, one gentleman is coming. He's a theoretical chemical physicist. Okay, and you can show, because he is a master's in quantum dot. He understands the theory. So why don't you prepare presentation and put it in front of him? So I prepared my presentation, and the gentleman came, Alan Bard came, our group sat, I presented at work, and that particular fellow was very happy because I have supported his theory of effective approximation. Effective approximation already supported by ultraviolet proton spectroscopy as well as other spectroscopy technique, but not supported by this way. Okay, first time electrochemistry we supported his theory of effective mass approximations, and the paper got published in next 15 days. Means today I submitted results, 15 दिन में वो आ गया, publish भी हो गया. Okay, JACS communication. I am not boasting myself. Why I told you this? Because that gentleman was Eli Bruce. Okay, and he was basically was actually the basically father of that quantum dots, and happened to be at Austin, and I happened to be there. It is all this maternity. सगळं जुळून आलं, and he accepted because Alan Bard would not have accepted, because he said I will not accept, because if I accept, he will blame me that I am asking my own student's paper. So that is the story. This JACS paper. Okay. Well, so immediately people got excited with these results, because for first time someone has shown that electrochemistry can be used for this purpose. Well, so a lot of You can see conduction band age, valence band age, and there are some intermittent states which are gives. We have interpreted this completely. We are completely backed the spectroscopy. Well, I'm going to discuss all the results there. You can read that paper. Well, there's one more theory I would like to discuss. Then we'll go for actual main content. The theory basically is suggested by Junger. When the quantum dots basically undergo charge transfer process, that means what? When we try to put the charges on the quantum dots, okay, we can classify into three types. Electron addition. Okay, I will not discuss this part, electron addition. It happens with some clusters. I'll focus on this, which you know. When a charge is formed within the quantum dots by shining the light. When you shine the light, what happens? If energy is more than the band gap, it will form exciton. Agree? This is the situation. But this is the situation here I shown you. Okay, here electron and hole in two different quantum dots. Here electron and hole pair are forming within one quantum dots. If they form within one quantum dots, then they will start interacting with each other because of Coulombic interaction. But suppose if I form the quantum these charge pairs in two different quantum dots which are infinitely away, then what will happen? They can't interact, and this process is called non-interacting electron hole pair. These situations occur in scanning tunneling spectroscopy, and we showed that this situation also happens in voltammetry. So when we form basically charge pair like this, it is called quasi-particle. It is called quasi-particle. So this process is actually forming quasi-particle, and quasi-particle has got different energy than this photo-excited electron hole pair. And difference is actually only by Coulombic interaction, J couple. Should I repeat? In case of normal situation which normally we encounter, electron hole pairs are forming within one single quantum dot, and they interact and form exciton. But in this situation, we form electron hole pairs in two different quantum dots, because in my case, oxidation is taking place in one electrode and complement reduction taking place in the other electrode. So my quantum dots are separated and forming a situation where they are non-interacting pairs. Now, the gap between these two is actually Coulombic interaction, quasi-particle and optical band gap. Normally we measure optical band gap in our situation. Here basically we are measuring the band gap without Coulombic interaction. That is my quasi-particle, and voltammetry give me opportunity to measure this quasi-particle. Well, we'll proceed. Now, I have put all these hallucinations, hypotheses, theories about quantum dots, about voltammetry, is it not? Now we'll go ahead with these ideas. Instead of cadmium sulfide, we prepared cadmium selenide. Okay. Cadmium selenide is narrow bandgap semiconductor than cadmium sulfide. Okay. So I got opportunity to prepare series of particle size. In cadmium sulfide is a wide bandgap comparatively. So if I prepare quantum dots, the bandgap goes to UV region. I don't want that kind of situation. I want everyone in the visible region. So we have chosen cadmium selenide, and prepared this cadmium selenide. We have prepared these sizes from 3.6 nanometer to about 1.9 nanometer, various particle sizes. You know that hot injection method? Bawendi, Nobel Prize. So that method could allow us to prepare the sizes of various sizes, monodispersed particle. So we have this particle, we have this absorbance and luminescence here, you can see here. So we have got now 7 fractions of various sizes of particle. Now I can study size condensation effect That means change in property with respect to size by voltammetry. The unique opportunity I have. Well, if you do that, this cyclic voltammogram, there is a solvent, there is a cathodic peak, there is anodic peak. Conduction band edge, valence band edge. LUMO, HOMO. Okay, then I change the sizes from big size to small size. Accordingly, peak position start changing. And then systematically, when you put it here, particle size versus the energy. This valence band, this is conduction band. The blue dots, blue dark dots and blue hollow dots are our results from voltammetry. Okay. The stars and triangles from other authors, they match very well. Okay. Dotted lines basically is not the eye guide, just not randomly connected. This is the theoretical description from Zungar et al. So our results not only match with spectroscopy, but also match with theories. Okay, that's the beauty of it. Any theory, beauty is that you should give the experimental proof. Well, this is another author actually done this experiment by ultraviolet photoelectron spectroscopy for cadmium selenide. And they refer our results to show their results, to support their results. Okay, they did by UP. Actually they are put, I think this black dots are our results and reds are their results. So they match very close. So they're very close. Some other people have done independently and results matches very well with the voltammeter. Well, there is one more author. Sorry. Again, he has done that for cadmium selenide. Again, results matches very well. Again, you can see they refer the Inamdar et al. You can see here, right? Inamdar et al. The diamond. Okay, and red dots are their results. They are quite close actually. They are very close. So not only one author, there are many authors supported our results by spectroscopic technique, and that is the strength of this technique. Well, I will not discuss anymore. I just have some different ideas here I try to put here. I was discussing about quasi-particle gap and optical band gap, and difference was J, Coulombic interaction. So here in this picture, the size versus band gap. The blue one is electrochemical band gap, and red one is optical band gap. Okay, when size decreases, you can see that the gap start increasing, and we measure the lowest size particle, 1.9 nanometer. This band difference. Okay, here. So that energy difference is nothing but equal to Coulombic interaction. And once I know Coulombic interaction, I can estimate size of exciton. Agree? Because size of exciton is equal to Bohr radius at that point. Okay, so I can estimate now using simple difference. I can estimate size of quantum dot. Okay, that's what we did here. And by using our method, basically, the size of quantum dots came out to be 2.3 electron volt. Okay, and actually, if you see in this case, it is one I didn't write here. It is about 1.9 nanometer. So they are very close to the TM images picture what we are recorded for this particular part sizes, and what estimated from this, both number matches very well. So what theory, Bruce theory we applied to our system work. Interesting part here. The smallest particle has got extra peak here, A2. I had A1, I had C1, but I have A2 here. In luminescence, I got again one shoulder here, photoluminescence. If I calculate the energy of that particular peak, it turns out to be 2.3 electron volt. If I calculate this energy for this peak, it comes to 2.5 electron volt. So these two numbers are very close to each other, which tells us that there are some states which are present between this band gap, okay, because of which I got a shoulder in the luminescence, and also that gave me a peak somewhere here in the cyclic thermograph. So there's a fantastic match between spectroscopy results and electrochemical voltammetric results. Well, so I will not stretch now anymore beyond this point. We tried many such quantum dots, okay, cadmium tellurides, what not we tried. We tried many, okay. So it works really well. Here we did DFT theory. I don't want to now impress you by showing our paper right now. I have no intention to impress you by showing such paper, but I'm trying to give you some results which match very well, match even the DFT theories. Well, so there's a lot of results. I don't want to discuss those results right now. So we did with these recent results which are not yet to be published now. The cesium layered mixed halides, we change the compositions by changing the halides. Okay, so many results are there actually. I don't want to discuss this. Again, here you can see, I don't want to really waste your time in showing the results. So again, there is a cyclic phototomogram based on composition of quantum dots. Again, there is a shift in the particular valence band age, conduction band age. Okay, valence band is changing more than conduction band age. That is big, and this is red dots are our results, and the blue and are other authors. Again, it match very well. We explain this by basis of this electronegativity of chloride ions. I don't want to discuss right now. We will proceed, but there is no new ideas in this result, so I don't want to tell you. Well, there's so many things: cesium, copper, zinc, tin sulfide, selenides. So many quaternary materials were tried and work very well with our so many. The zoos actually, I can show you. So many. I'll skip all these things. I'll skip. Well, this is important slide. Now you must be worrying. Actually, this whole measurements is done in non-aqueous solvent, like THF, okay, propylene carbonate, DMSO, DMF, and my electrochemist worst nightmare in such experiments actually is the moisture. Traces of moisture there in the solvent is going to give huge peak in the cyclic thermograph. So we want the measurement to be done in very dry atmosphere, no moisture. And I came from a very poor laboratory. I don't have glow box. I didn't have glow box actually. I have now. I didn't have glow box, and you have to do this experiment in glow box, organ-filled glow box, which I did in the US. So now, how would you overcome this difficulty in our very poor small laboratories, where hardly any facility? So what we did, I scanned old paper publication from inorganic chemistry. Okay, and inorganic chemists also need such a dry atmosphere, especially few metal complexes. So then I found that they are using very unique way of making these complexes in an atmosphere, and we adapted this idea to our problem. Idea is very simple. We use electrochemical cell. This is a cross section. There are 5 ground glass joined to electrochemical cell. Okay, and there's a jacket cell. You can see jacket. What we did now here, we added in this. You can see there is a counter, reference, and working. There is a argon and vacuum, two-way gas, and then we added basically supporting electrolyte, which is TBAP. Normally we add. We need supporting electrolyte in electrochemistry to make the solution conducting. And we heated this by passing the hot water, so that now my cell temperature become 80 or 90. And now I apply vacuum. So what will happen now? In situ, I am drying my supporting electrolyte, because there is a temperature is 80-90 and applying vacuum. So once I dry my supporting electrolyte in C2, then I added the solvent, injected the solvent and the quantum dots. And again I have applied the vacuum and argon, vacuum and argon 3-4 times, so that my atmosphere now become moisture free. And then we did the experiments. One more problem, we can't use our AgCl or calomel as a reference electrode in a non-aqueous solvent. Because why? Because those electrodes are aqueous base. We can't introduce, we don't want even traces of moisture. And I can't put whole electrode, aqueous electrode in the non-aqueous solvent. Okay. So normally what we do, we use a quasi reference. We use a silver wire as a reference and do all the measurements. Okay. It's not real reference, it is a quasi reference. And then by using ferrocene, okay, we are standardizing the, once we bring all the experiments, we add ferrocene. So I can now calibrate all the potential with the redox potential of ferrocene. That's why our potential is very accurate. Okay, I thought I will share this. I'll take 5 minutes break and maybe you have a time with what time?
Otherwise, you may continue.
I'll continue.
Yeah.
But I'll just drink water, 1 minute.
Yeah. If you want break, then we'll take it.
I'll continue. They also must have exhausted by all these theories. Don't get up. We'll just keep silence for half a minute and we'll continue. Any question in this gap, 0 hours you can ask. Any questions? एकच मिनिट दुसरं प्रेझेंटेशन आणि नाही काहीच नाही एकच मिनिट पुढचं करूया प्ले कर हा प्लीज
Sir, in semiconductor material, means whenever we shine light or when we thermally excite, we give energy to semiconductor material, there is always formation of first exciton and then electron hole pair, right? Means first
electron hole pairs are exciton.
Means first exciton form and then they separate.
Both are same. Electron hole pairs are exciton.
Okay.
When electron hole pair come, basically once you pair means what? They are pairing, no? Electron holes are pairing, which is exciton. Nothing like that. There are two entities like electron hole pair and exciton. They are one. The way we call them, no?
Okay, and one more thing about band gap measurement using CV. So you said we have to give positive bias potential, negative bias potential. Means overall in one CV we are getting all those information.
Yeah.
Right. Means if there are many peaks, so how we have to consider which is HOMO and LUMO peak then?
No, this is a very cyclic voltammeter that way gives a lot of gray areas. They pick a lot of peaks, but peaks which are repeatedly coming in the voltammogram, you have to consider. If you do 10 repetitions and then you realize which peak is genuine one, which peaks are not genuine one. हाँ बोला. I'll spill over about 15-20 minutes after 1 o'clock. Huh? No.
Sir, as we can see that as the size of the quantum dot decreases, the area under the curve of CV curve is also decreases. We can see as the comparison in the CV curves, like.
See, area under the curve depends on many factors. We'll not consider that right now.
So
nothing to do with area under the curve. In spectroscopy, it is yes true, but not in cyclic voltammetry.
So because my application is supercapacitor application, so as the electrode, the surface area depends on how the CV area under the curve, we say it as surface area increases, the area under the curve of the CV is also increases, as we can see in the literature. So I want to know, here we can see that the band is going shifted here. So what about the area? So what is the mechanism we can see here?
Area depends on many factors. One factor is basically the dispersibility of the quantum dots. Okay. Area under the curve tells you number of coulombs actually. And I don't think so, because size has no relation with area under the curve. As theory I know, there's no relation.
Okay.
Area under the curve, cyclic tomogram depends on some other factors. See, for them, for cyclic voltammetry, it doesn't care whether quantum dots hai ya di molecule hai ya some other. They just see what it sees, whether there is a orbitals which can accept the electron. So that accept the electrons, the tendency will not change with area. The area under the curve will not change with the size.
So area doesn't matter here.
Doesn't matter area under the curve.
Because as the area increases, the current is also increases this side, no sir?
I think you are mixing with supercapacitor with this concept.
No, I want to know about the mechanism for the surface area, like for the
just
CV.
ask a straight question. Don't relate with this. Ask a straight question.
Sir, as the quantum size decreases, we can
supercapacitor. Ask supercapacitor.
So if something I added to the some material, what happens is that the area under the curve of the CV increases. Diffusion.
Area under the curve basically depends on many factors. Okay. In supercapacitors, your 2D materials.
Yeah.
The diffusions, have you measured the impedance spectroscopy? Must have done. So Wahlberg impedance basically has two parts. One diffusion is from solution to the electrode, and electrode inside the collector.
Yeah.
Because of 2D structure. So area under the curve basically as I said by also diffusion. There are many factors which affects area under the curve.
Okay.
Not one single factor like size of the particle.
So size is not only the matter. Okay.
Area under the curve just tell you number of coulombs. That's all.
So, how the direct band gap and indirect band gap makes difference in the solar efficiency?
Yeah, I think Prashant was right person to ask this question, but still I will address now. See, when the exciton forms, see, in case of direct band gap semiconductor, his question is now how the indirect band gap, direct band gap affects the efficiency. See, when you excite, see, one photon should give one electron hole pair. Agree with me? So, it's most efficient system. There are some semiconductor which give more than one electron hole pair, like lead selenides. Okay, they give more but more the electron hole pair, more the efficiency, because एक photon से चार बन रहा है exciton, अच्छी बात है ना, तो minimum एक तो बनना चाहिए. But in case of silicon, I will go back or I remove this. In case of silicon, it is an indirect band gap semiconductor. Means what? If you see Brillouin zones, physicists know Brillouin zones. So basically, their momentum is not conserved in physicist term. Means what? Unless there is no conservation of momentum, the energy will not transfer from photon to electron, fermions. Okay. I hope I'm close to you. So what will happen here now? To create one electron hole pair in silicon, you need more than one photon. So when you shine 5 photons, you get one electron hole pair. So inherently system is inefficient. We want at least one electron hole pair, right, for one photon. But silicon gives 5 photons require one electron hole pair. 5 is a random number I chosen. Okay, that means what? The system is inefficient. The semiconductor is indirect bandgap semiconductor. But in a direct bandgap semiconductor, this process is very, very efficient. Okay, as I told you, one boson, one proton, one fermion, one electron hole pair.
What about the stability of
That's $1 million question. Stability of quantum dots. The challenge with quantum dots basically, as I told you, that when you give the charge to the quantum dots, they undergo chemical reaction followed by electron transfer, and that basically degrade the quantum dot. That is the challenge of whole field of quantum dots and solar cell. So they undergo degradation not because of light, because of chemical reactions. Once they get electron, they are so hot electron, they can't hold a hot electron with them. Okay, they have tendency to undergo chemical reaction. So stability of quantum dots only because of this chemical reaction followed by electron transfer. So always there is always whole this thing jeopardize the solar cell efficiency. So by some time your solar cell efficiency come down because the active material start degrading with time. Even with this perovskite, so much hype about perovskite solar cell for last 10 years, right? Everyone is working on perovskite solar cell. Is it not? Challenge is basically it is not thermodynamically stable system. It is kinetically stable system. It exists for some time, but it will not remain stable forever. We are kinetically stable, right? We are all mortal people. We are going to die one day. Is it not? But in between that, we have some stability. We live like we are going to live forever. Still we always wonder why this person died. But we never thought that, "Arey, maybe barne wala within." So, problem with this is kinetic stability. Many materials which are very good, okay, but they are not thermodynamically stable. Even this cesium, even this another material, cesium lead iodide. Challenge again that phase we are referring to basically is kinetically stable, not thermodynamically stable. Shall we proceed with next ideas? Okay. Next idea basically is how to approach energy research. We are already discussing this, and we are already discussed this slide. Is it not? Yes, various techniques. So I think we have at least understand a little bit about cyclic voltammetry in energy research about quantum dots. We understand, I believe it is percolated a little bit here and there with you. Now I am going to tell you complete different technique called scanning electrochemical microscopy. Okay, SECM. Well, these are basically the variables in electroanalytical techniques. Variables. What are variables in electroanalytical techniques? I have potential, I have current, and I have time. Whole game basically I am playing with these three variables: potential, current, and time. Well, based on their combinations, when you combine two, I will keep third constant. Always. I vary two, I'll keep third constant. If I do that, play that game. If I change basically a potential and measure current, we call voltammetry. If you change the potential and measure current, it is called voltammetry. We know that. If you measure current versus time for constant potential, we call chronoamperometry. Chrono means time. Chronoamperometry. Here basically we are measuring current versus time with constant potential. Then we have measuring potential versus time with constant current. It is called chronopotentiometry. So we have chronoamperometry at constant potential. I have chronopotentiometry at constant current. To measure chronopotentiometry, you need galvanostat. Some of you must have having a potentiostat, galvanostat. You understand potentiostat, but many students don't know what is galvanostat. So in galvanostat, basically you can control the current and measure the potential. Potentiostat You control the potential, measure the current. So I have chronoamperometry, chronopotentiometry, cycle voltammetry, already we have seen this. I have now one more technique where I am measuring the probe current versus distance. So I am introducing one more variable here, distance. So initially, traditionally, I have three variables, current, potential and time. Now I am introducing one more variable, that is distance. Distance between what? I have probe and I have a substrate, and I am going to change, I am measuring the current as a function of distance between probe and the substrate under investigation, that is electrode. I will explain to you. तुम्ही बदलताय का? हाँ? नहीं, it's okay. अब संपत आहे आपले. Well, so here, atomic force microscopy. You know that, right? AFM. Some people always have some infatuation with this AFM technique. I will not say attraction, infatuation actually. Here, basically, people think that if I get AFM, I can see the atoms. Misconcept. Okay, here basically we measure the force between the probe and the substrate. It is basically a physicist technique which measure force versus distance. And sometimes we can use this as a microscopy. That's why it's called microscopy. But actually it is a physicist technique which measure the van der Waals interaction or London forces, attractive forces between the probe and the substrate. Very close distance. I have another technique which also through which we see the atoms, that is scanning tunneling microscopy, STM. Okay. Here, but for this we need conducting substrate like metal, gold metal. Okay, and here basically you are measuring tunneling current, you know tunneling effect, right? Particle in a box problem. Go back to particle in a box problem where your wall is limited, where energy is not infinite, energy is finite. Then what will happen? There is a finite probability of finding electron outside the box due to tunneling effect. Remember this? Particle in a box problem? लोग डरते हैं actually quantum chemistry बात करते हैं. Well, so, but I am not a person. I'm poor electrochemist basically. I understand a very limited thing. Well, so here in this case, tunneling effect between the probe and the conducting substrate. And here, really you can see the gold atoms, STM. And now we have our beloved scanning electrochemical microscopy, where my probe is not the cantilever, my probe is not the tungsten wire, my probe is actually the micro electrode. Chota wala platinum electrode of micron size. Okay, and now I am bringing the probe to the substrate. Substrate could be conducting, semiconducting, insulating. Systematically I am bringing down. Okay, and I am getting some contrast. I am getting contrast due to difference in redox activity happening between probe and the substrate. Sorry, I have forgotten single breath. Basically, there is a redox activity going on the probe and a complement redox activity going on the substrate, and I am measuring the difference between these two redox activity and get contrast. Contrast will tell you some part of the substrate is electrochemically active, some part of the substrate is electrochemically less active. So I can now map the electrode. In mapping, I can determine this part is active, this part is not active. We'll go to see in more details. Well, there is a, why do we need SCCM? We can now measure the rate constants of electron transfer without applying any potential to substrate. So I have a substrate and I have to study kinetics of charge transfer. So what electrochemistry does? It will bias the electrode. Is it not? I have some semiconductor film I have to investigate, impedance spectroscopy for example. What I will do? I will apply the potential. But once you apply the potential, my film will start degrading with time. So I don't want that. But without biasing the substrate, I can measure the kinetics parameter, the rate constant of charge transfer. I can bring the probe and measure. I can image the cell's biology. In biology, many people now use SSM for imaging the live cell. I can also draw some patterns by using SSM. We are not going to do on all these details. They're all fancy things. Okay, we'll just focus on this part. The heart of this SSM is ultra micro electrodes. The very small electrode. Okay, in the glass shell, the platinum wire is sealed, and diameter of the wire is about 1 to about 25 micrometer. They're very small. You need a microscope to see the platinum wire. It is almost like 220 times thinner than our hair. Okay, it is called ultra micro electrode. And this is the cross section of this. How does it look from the side? There is a ray diagram. And under the microscope, we can see the bright spot is platinum. ऐसा देखते हैं, ऊपर से देखते हैं. The cross section. So bright part is platinum. So why microelectrode? Because since my electrode is small, it will draw very tiny current. It will draw nanoamps or picoamps. Then what will happen then? Once my current is small, my IR problem, I think some of electrochemists know IR drop. What happens there? Because of current and resistance or potential shift, it is called IR drop. So my current is small, my IR drop is very small. So deviation from actual potential is small. So I can actually measure accurate potential by using small electrodes. Bigger the electrode, more deviation. Smaller the electrode, less deviation. Still smaller, ultra small, still less deviation. So when do you do electrochemistry, you should not pass milliamps of current. Students are doing pass milliamps of current and try to record cyclohothermogram. See, normally in electrochemistry, smaller the better. So try to choose as small as electrode, which will give more accurate results. So it is really small. It is micron. So its potential is very accurate. Area is small. So capacitance is small. If capacitance is small, the error in the potential again small. The capacitance of the interface gives again error. So we don't want capacitance. We want Faradic process. We don't want capacitive current. Because capacitive current gives you the error. Why capacitance is there? Because there's interface. The charge interface. You learned that, right? There's capacitance. So that will add into the potential. So you don't want that. So all this problem which electrochemists face because of macro electrode can be eliminated by micro electrode. So all by measurements in my lab, basically we try to use smallest the possible electrode, very, very small electrodes to avoid these problems. So that's what I'm telling you. You should not supercapacitor, someone is telling me. No? So if you use big electrode, supercapacitor, you're bound to have some problem. So make the electrode of 2 millimeter by 2 millimeter. Try to make an electrode. Very small. Well, let us see the interfacial dynamics at macro electrode. When my electrode is in millimeter diameter, this is a cross section basically. It's a glass shell, platinum wire and a glass shell. The cross section. And when I polarize this electrode, apply a bias in the redox, what will happen? It will form depletion layer. We see depletion layer. We saw depletion, right? The redox concentration decreases when I apply potential near the interface. It is called depletion layer. But now my electrode is so big and my depletion layer is in micrometer size. So very thin, like I'm putting chatai on this in this floor. Very thin depletion layer compared to the size of electrode. My electrode is in millimeter and my depletion layer is in micron. Very thin. So obviously my linear diffusion will dominate. My mass transport of redox will be through diffusion. You learn, right? Diffusion. So diffusion will be linear, one directional. Okay. But suppose if I use micro electrode, I think it's a date time always. Okay. So this kind of response you get for cyclohologram for macro electrode we've seen already. But if I choose micro or ultra micro electrode, now my electrode is in micron and my depletion layer also is micron. So now my depletion layer is comparable to that of electrode diameter. What will happen now? Instead of linear diffusion, I have spherical diffusion. Okay. And if I get spherical diffusion, because now my diffusion layer is very small compared to my electrode size. So I have got diffusion from all the sides. Okay. And because of which I get kind of this kind of response. Like polarography, you used to get response, right? Because spherical electrode. You remember polarography, learned in BSc? Polarography, S-shaped curve. So you get S-shaped curve for micro electrode instead of cyclohologram like this. Okay, it is called steady state response. Well, so this is the actual steady state recorded basically for some redox with micro electrode. The way we expect you get such a response. Well, now we will do some experiment here now. What we'll do now, I have ultra micro electrode, I have redox, my electrode is biased, polarized, so that redox reaction is occurring on the surface, maybe ferric to ferrous or K3 to K4 I'm sufficiently biased the electrode so that I'm getting some reaction on the surface. Okay, what kind of response we get for such electrode? Already we have seen a steady state response. But suppose I have mechanism to bring this electrode down like this. Okay, and here is the substrate. My substrate is insulator. Let's say Teflon is the best insulator. And if I bring this electrode from infinite towards the substrate slowly like this, my experiment is like this. My electrode is polarized in the solution. In the solution I polarize. My redox reaction is occurring on the substrate on the EME ultra micro electrode. And I'm bringing the electrode down like this. And what will happen when I'm very close to the substrate? When I'm very close to the substrate, what will happen now? It is less than a micron close to the substrate, then it will hinder your diffusion. Now, redox cannot reach to the electrode because already it is a block. Because my substrate is very close, right? So my redox cannot reach from bulk to the electrode surface. So obviously my current will decrease, right? Because there is no redox near the electrode surface, my current will decrease. It's a unique problem I have seen. सगळं लेक्चरचं कंटिन्युटी जातलं मध्ये मध्ये. Well, so when I come very close, my current decreases because of called hinder diffusion. My diffusion is hindered. My redox is not able to reach toward the electrode surface. And this kind of response, this infinity is a distance. When I am infinite distance, I get normal response. When very close, that is zero, reduced response on insulator, that is Teflon. Suppose, so if I do this experiment very systematically, in animation, my electrode with spherical diffusion, this is my ultra micro electrode, this is spherical diffusion, this is my insulating substrate. So when I bring this electrode very close to the substrate, and here is the response, tip current, that is ultra micro electrode current versus distance. You can see current start dropping down when you close, very close. Obviously because of hinder diffusion. It's very simple to understand. Okay, but suppose now if I use conducting substrate like platinum electrode, then what will happen? Here's the conducting substrate. Again, same experiment, ultramicro electrode, redox, polarized or biased. Again, I have response the way I got before. When distance is infinite, is a distance. But now, if I bring this electrode again the same way I bring close, what will happen? चालत अजिबात चालत कसं काय मी इथेच उभं राहू का मग? Well, here basically your response at infinity, but when you bring this ultramicro electrode near the conducting substrate, current step up 10 times. Previous case, when my substrate is insulator, current drops down and obviously hinder diffusion. But when I bring this same probe to the conducting substrate like platinum, current step up. The question is, why current step up? It should also hinder diffusion. The substrate is going to hinder the diffusion. But what is there in the platinum or conducting substrate which increase the tip current? Remember, your conducting substrate is not biased. I didn't apply any potential to the platinum. So why this now response to the tip step up? Here is the response. Again, I have ultramicro electrode. I have spherical diffusion. Okay, and conducting substrate, and is a distance between substrate and the tip, and this is a tip current. You can see it increased 10 times. So conducting substrate basically actually give positive feedback. My insulating substrate gives negative feedback. I am giving you vocabulary and then we'll discuss actual results. So my conducting substrate gives positive feedback, current increases. My insulating substrate gives negative feedback, okay, which current decreases. Well, so now we'll answer this question, why this conducting substrate step up the current. Okay, this is a typical situation where this is my substrate, platinum, and this is a cross section of ultramicro electrode. Just beneath the micro electrode, just beneath, okay, my O is getting into R. So just beneath, concentration of O now is less here, right? Because my O is getting into R. So if I leave that electrode close to the substrate, my O is getting reduced to R. So concentration of O will decrease just beneath the platinum. But away from platinum, somewhere here, there still basically nothing is happening that side. So now concentration of O is less, R is more, and it is normal concentration. So actually it forms the concentration cell like this, where in one compartment the concentration different than this compartment. We learned this concentration cell in your BSc days. Okay, and this concentration cell actually drive the electron pump. Okay, and now that potential is sufficient enough to convert R back into O. So now O is available near the electrode. So you get more current. It is called positive feedback. So forget about all these theories. Remember this for you as analytical technique. Platinum electrode gives positive feedback and insulator gives negative feedback. Now we know the rules of the game. Let's move with these rules. Well, now I can now fit into some theories actually. I can fit these theories. And these dots are experimental points and lines are theories. Okay, I can do this fitting, whole experimental points in the fitting actually. So my experiments goes very well with the theory. This is for conducting substrate like platinum gives positive feedback and Teflon substrate gives negative feedback. Well, and there is one more thing here. There is an in-between feedback actually. Neither clear negative or nor clear positive. It gives in-between because of if a rate is this transfer of electron here is here on the substrate is slower than this, that means Ks is smaller than Kt, then actually we'll get in-between feedback. It's called immediate feedback, and it's very useful. Actually, I can now determine the rate constant, effective rate constant of charge transfer. So now again, don't worry about this equation theories. Rule of the game is I have positive feedback, I have negative feedback, and I have got in-between feedback. In-between feedback is useful to determine the rate of charge transfer. Okay, well, let us very beloved material of a very poor chemist, that is graphene oxide. Okay, is it not? बच्चे आके एमएससी के बच्चे आके ग्राफीन ऑक्साइड बनाते हैं लैब में. So graphene oxide basically now, you know, it is semiconductor, is not really conducting or not really insulating also, in between somewhere, graphene oxide. Well, so now I'm going to very simple design of experiment. Graphene oxide in nascent state as prepared, and graphene oxide after reduction. What happens? Ekdam simple. And what happens means whether there is conductivity changes. So how I'm going to measure? SCCM. It will bring the SCCM probe, and then if I get positive feedback, I say there is a conductivity is there. If you give negative feedback, I'll say it has got no conductivity or less conductivity. Agree? Like if you give pumpkin to the carpenter, carpenter's wife give pumpkin to the carpenter. This is a problem to make the pieces. But carpenter is very unique. He will not cut that pumpkin just like that. He will take the pencil, he will get the putty and then make the lines, exact typical lines, and then he'll cut. Okay, this problem is like this. Conductivity I am measuring with SCCM probe. Okay, well, we can measure directly 4 probe also. Put 4 probe and measure it. Well, so this is the experimental design. I have graphene oxide, I have basically redox, and now I'm bringing the SCCM probe approaching to the graphene oxide, and if this fellow is not that conducting or not electrochemically active, now I'm changing the language, conducting and electrochemical active. If my film is not electrochemical active, then I expect negative feedback. And suppose after reduction also is done by electrochemically, by after a negative bias, and if I do that, okay, I will get positive feedback. That's a hypothesis. Okay, take film, measure the SCCM, expect negative feedback, then I polarize this graphene oxide, expecting that will reduce into reduced graphene, and reduced graphene should give me a positive feedback. This is the MSc level experiment. Well, this is the cyclohottomogram of graphene oxide. It indeed gives some cathodic current, which tells me that it is undergoing reduction to reduce graphene oxide, and that can be checked by Raman spectroscopy also after reduction. Well, and then what we did, we measure the SCCM approach curves at various reduced state, applying minus 0.2 volt, minus 0.4 volt, minus 0.8 volt, and doing the measuring the SCCM. And you can see here, initially the probe was negative feedback, and once it's reducing more and more, it starts showing the positive feedback. Okay, in fact, we measure the effective rate constant by using limited approach curve, in the in-between case, determine the rate constant of charge transfer. I'm not saying in physical chemistry out of it because no time in telling physical chemistry, but by using very simple technique, we could measure the charge transfer rate, how fast it undergoes the charge transfer. There are many such examples. I'll give the example and stop, because this whole conference on energy, right? Solar cell. It's a very interesting experiment we did there. Here is the cadmium sulfide quantum dots. So we sprinkle cadmium sulfide quantum dots on the glass film, glass sheet substrate. So I have got now cadmium sulfide quantum dots on glass, very thin film. And now I can immerse this into electrolyte, and it forms Schottky junction like this. You understand, right? Schottky junction. Physicists understand Schottky junction. So what will happen now? If I expose the junction to the light, what will happen? Electron hole pairs will separated. The electrons will go slide down in the bulk and hole will bubble out in the solution. We learned, right? If I put the semiconductor in the right redox, I will get this junction, and Schottky junction, if you expose the light, I can separate the electron hole pairs. That's the basis of solar cell, and then my electrons will roll down and hole will bubble up. We know that. The hole which is bubbling out, now I can choose some scavenger for hole. Amines are normally act as scavenger. They take away the hole very fast. It's a triethylene amine is used as scavenger. So hole will taken away by the scavenger, leaving electron on the semiconductor. Okay, and the electron I can use here is process now. Charge transfer, recombination, scavenging hole, and now I can use methyl halogen. Methyl halogen I think is very good redox. Some of you must have heard, right? Methyl halogen. Methyl halogen is used basically as a pesticide on the wheat normally in the US. It's very expensive but very effective pesticider. We don't afford here in India, but it is a pesticider. So methyl halogen basically when you reduce, it becomes very dark blue. Okay, very dark blue color is formed because of formation of radical anion. Well, so methyl halogen basically is the redox. So now I can now reduce the methyl halogen in the solution by those electrons. So now I have the mechanism. I have set up the experiment where I can measure now the charge transfer of electron transfer from semiconductor to methyl halogen. The whole setup is like this. Whole plot of the drama is like this. Is a plot. Well, so idea now is the next. Yeah. Here now again I have got cadmium sulfide film, glass, methyl halogen, SCCM probe. Okay, and back illumination. Just put light down. So now I am exposing the interface with the light and generating for electron hole pair. My hole will be scavenged by the hole scavenger, TEOA, triethylene amine, and electron will be taken by the methyl halogen. And methyl halogen will now shuttle the electron between my film and the SCCM probe. And now I am going to measure response of SCCM probe because it has got information, that current has got information about the rate constant, K effective. So eventually I am measuring the rate constant of charge transfer by using SCCM probe for this simple photoelectrochemical setup. Here is the experiment, and in a dark there is no charge pair, no electron, no methyl halogen reduction. Okay, and you get negative feedback like insulator. But when I expose this to the light in the illumination, under illumination, it starts showing the positive feedback. And now I can measure the effective rate constants here. The various variables actually I can use here. I can change the light intensity, I can choose the methyl concentration, I can choose the TOA. Forget about all these variations. Okay, so I can measure, in principle, I can measure the effective rate constant of charge transfer, in which I am interested in always as a physical chemist. I am always interested in kinetics and thermodynamics of charge transfer. Well, I think you are already exhausted, so I don't want to. So far we have bringing the probe from the z-axis like this. But now imagine I can bring the probe down and then start rastering. And what will get? I'll get some image. I'll get some 2D map of the electrode. Okay, there are hills, more current, where there is a charge transfer, and there are valleys when there is a negative response. So by just using hills and valleys, I can now map the electrode surface, which part is electrochemically active, which part is electrochemically not that active. Understood? So Well, so this is the way I can move the electrode on the now x-axis or y-axis about the substrate. If there are hills here on the substrate, the current will hinder and I'll get down current here along that axis. And if my surface is very active, electrochemically active, I get hills like this. So I can generate the map of the electrode surface, because on electrode surface, not whole electrode is active. Some part is active, some part is not that active. Okay, well, so here is a plot of the drama. Now we are using basically carbon fiber of micron size, and we found that it's very active. We made actually the single fiber electrode like this of carbon fiber when Shivaji was there when we were doing experiment. So this electrode basically are one strand of carbon fiber, very small. We have to see under the microscope, thinner than our hair. And then we attached to the substrate and did a lot of voltammetry to determine dopamine concentration. Basically, the idea here is that people used to use microelectrode to determine dopamine concentration in the brain. What they should do, they drill the hole to the brain, of course mouse, and then they put the electrode and measure dopamine concentration. That was experiment done by biologist. So we developed some microelectrodes for that experiment, those experiments. And we measure the dopamine concentrations basically. Okay, it will be very difficult otherwise to do it. Well, idea is not that. What we did, idea was basically that time there was debate that which part of carbon fiber is active, whether graphitic plane is active or there are defects which are active. Which part of the carbon fiber gives that response? That was the question. So what we did now, we have basically this is a carbon fiber, okay, and we now again did the same experiment on a single strand of carbon fiber lying on the glass substrate. And what we find that the response of that are uniform. Some part gives strong response and some part gives less response. When you compare these optical images, there are some black spots on the carbon fiber, and those black spots basically are active. Now, what are those black spots? When we try to analyze it, we found that those black, we have taken the Raman spectra of that particular black spots and found that those are defects. It is basically pseudo sp3 hybridized bonding halfway. You know that graphitic carbon has got sp2 hybridized, and some part is also sp3 hybridized at the edges. You know that, right? So this is basically pseudo sp2 hybridized bonding. Okay, and those unsaturation in the bonding actually act as a catalyst, not the graphitic plane. Well, so a lot of things I will not discuss. This is only platinum wire, doesn't give such a response as a control. And there's various theories we did and determine the K effective, the rate constants of charge transfer. I don't discuss this part. I think it's a time to stop. Okay, and because I don't want to stand between you and lunch, you must be hungry, and you must be seeing as a kind of villain who is standing between the lunch. Bhook lagli ani hapudi male something like that. Well, there are a lot of people have done such similar. We're not the only people. There are many people. The Bard's group has a lot of experiments actually. Short stand. Pass. Here is important slide. Okay. Here is basically I would like to acknowledge various people here. My mentor Prashant was there in the morning, right? So I spent 1 year with Prashant's group about maybe 10 years back. Well, there is through basically Fulbright fellowship, and Professor Deleker, who has given me such a nice hospitality and invited me and give me opportunity to stand in front of you and share some ideas. Okay, and there are past students, red students are actually marked here, are basically what experience I have discussed from last 1.5 hours. Okay, and you can just Google or maybe go to ACS site and just give my surname, you will get this all papers were published in this particular field. Well, there are funding agencies and these are our group here. Okay, the group is actually old, not about after Shinde Sarkar came. Okay, the ENT were doing before that also. So here basically are people around and students and me. Okay, and now we have to recognize where am I standing there in this whole picture, where I am exactly present. Can you identify? Last question, then I'll stop. What do you think? This guy? This guy? Huh? कोण हा अब हा एक उभा आहे ना माणूस आहे इथे हा बघ तो काहीच करत नाहीये तो बोटं दाखवतो इकडे तिकडे बघा तो मी आहे okay rest basically are my students who have done all this work and I am just here just showing all these things. Thank you very much for your kind attention. If you have question, I will take for some time, 5 minutes more.
Cadmium sulfide and cadmium selenide, both the cases, where is the quantum confinement more? How it will be down here in that? Because sulfide and selenide have different properties. As per as the chemical reaction is not so particular. So where is the quantum effect is more, and how it will affect on the
So you are asking me questions, quantum size quantization effect and the and electrochemical activity. See, actually, these questions, actually we are not measuring kinetics. Actually, we are not interested here in quantum confinement, the peak height. Peak height has got information about the kinetics. More current, more kinetics. More current, more kinetics. But we are not now focusing on the kinetics, we are focusing on thermodynamics, the peak position. Sulfide and selenide, question is sulfide and selenide have got different activities. So why currents are different for those activities? Should be different, because everyone has different redox potential, and redox means selenide might easily get oxidized than sulfide. Tellurides are still easy to oxidize than selenides. So obviously that effects are going to be there. So that effects can be seen where your oxidation peak is more for tellurides, followed by selenides, followed by sulfides. But we never compared, but definitely will go and compare that part. Thanks for that suggestion. Thaklat.
Thank you for the wonderful lecture, sir. Now, I request Professor S.S. Kolkar, sir, to felicitate Professor Santosh Haram, sir, by offering Memento Shawl book as a token of gratitude.
Thank you very much for your attention. I hope I tried my level best to give that all ideas. Actually, we discussed many ideas in this process, not single idea. But I try to focus on idea rather than the actual results. So many ideas, so many possibilities for electrochemist. Okay, you can see here.
So please go on stage.
Thank you. Thank you. Thank you, Professor.
May I invite Dr. S.N. Taide, sir, to felicitate Professor S.S. Kolkar, sir, by offering Memento Shawl and a book as token of love and respect.
I'll go down there.
Take photo. Shivaji ka. Thank you.
it's very exciting moment for me to getting photographed with my student who is excited and taken electrochemistry as a career option.
Really, really.
It's all because of you, sir. Thanks for teaching me those.
We are all on satellite sector.
इंटरव्यू मध्ये मला क्वेश्चन सेम विचारलं होतं विच इज युअर करियर ऑप्शन सो येस
We are done for today's session and it's time for lunch. But before that, I would like all the participants to know some instructions. After lunch, we have arranged a visit to the SAIF Center for all the delegates. After lunch, please make sure to visit the SAIF Center.